Welcome. Take a deep breath, settle in, and prepare yourself for a journey into one of the most fascinating and pervasive forces shaping our world. Tonight, we explore corrosion, the invisible enemy all around us. Close your eyes if you'd like. Let your mind wander through the landscape of our modern civilization. Picture the bridges you've driven across, the buildings you've entered, the pipes beneath your streets. Now imagine that all of these structures are engaged in a constant, silent battle. A battle against an enemy that never sleeps, never stops, and exists everywhere. Let's begin with a staggering reality. It has been estimated that roughly 30% of United States infrastructure is affected by corrosion at any given time. 30%. Think about that for a moment. Nearly 1/3 of all the bridges, pipelines, water systems, and structural assets that form the backbone of our society are experiencing some form of deterioration right now, at this very instant. This isn't a recent development. It's a reflection of something deeper: the widespread age and exposure of our infrastructure. Many of the bridges you cross were built decades ago. The pipelines carrying water, gas, and oil beneath our cities were laid down generations past. And all of them, every single one, has been exposed to the elements, to rain, to humidity, to temperature changes, to the very air itself. Corrosion doesn't discriminate. It attacks the old and the new alike, though age certainly makes structures more vulnerable. A bridge built in the 1950s has endured 70 years of weather, traffic vibrations, and chemical exposure. Each year adds another layer of stress, another opportunity for that invisible enemy to advance. And what does 30% mean in practical terms? It means that at any moment, engineers and inspectors are monitoring countless structures, watching for signs of weakness, scheduling repairs, and hoping that they catch problems before they become catastrophes. But corrosion doesn't just threaten our convenience or our wallets. It threatens something far more precious. Corrosion-related leaks and failures in industrial facilities can trigger fires, explosions, and structural collapses, directly threatening worker and public safety. This is where the invisible enemy becomes visible in the most dramatic and tragic ways. Consider an industrial plant, a refinery, perhaps, or a chemical processing facility. Miles of pipes carry volatile substances under pressure and at extreme temperatures. These pipes are made of metal, and metal corrodes. A small weak point, a patch where the protective coating has worn away, a spot where moisture has collected. Any of these can become a failure point. When a corroded pipe ruptures in such a facility, the consequences can be catastrophic. Flammable materials ignite. Toxic chemicals escape. The initial failure can cascade, causing secondary explosions, spreading fire, bringing down structures. Workers who arrived that morning for a routine shift suddenly find themselves in mortal danger. And it's not just the workers inside the facility. When industrial accidents occur, entire communities can be affected. A cloud of toxic gas can drift over residential areas. An explosion can shatter windows miles away. A fire can burn for days, filling the sky with dangerous smoke. All of this from corrosion. From that patient, invisible process of metal slowly breaking down. The threat extends even into our homes, through the very water we drink. Corroded water pipes can leach harmful metals, such as lead, into drinking water, increasing risks of neurological damage and other serious health issues for exposed populations. This is perhaps one of the most insidious effects of corrosion: how it can poison us slowly, without our knowledge. Lead pipes were once standard in plumbing systems across America. Even after we learned of lead's dangers, millions of these pipes remained in service, buried beneath streets, running through the walls of older buildings. As these pipes corrode, lead particles and ions dissolve into the water flowing through them. The human body cannot easily eliminate lead. It accumulates, especially in the bones and brain. In children, lead exposure can cause developmental delays, learning difficulties, and behavioral problems. In adults, it contributes to high blood pressure, kidney problems, and cognitive decline. And lead is just one metal that can leach from corroding pipes. Copper, iron, and other elements can also enter our water supply through corrosion, each carrying its own health risks. The truly frightening aspect is that you cannot see, smell, or taste these contaminants in most cases. Families drink the water, cook with it, bathe in it, never knowing that every glass is delivering a dose of heavy metals into their bodies. But the reach of corrosion extends beyond human health. It touches every living system on our planet. Corrosion-related failures can release contaminants into soil, water, and air, damaging ecosystems, destroying habitats, and contributing to air pollution and respiratory problems. The environmental toll of corrosion is measured not just in dollars, but in damaged landscapes and disrupted life. When a corroded pipeline fails beneath a river, crude oil spills into the water. Fish die. Birds that feed on those fish are poisoned. The oil coats plants along the riverbank, killing vegetation. Microorganisms in the sediment are overwhelmed. An entire ecosystem can be thrown into chaos by a single corrosion failure. When storage tanks corrode and leak, industrial chemicals seep into the ground. They contaminate groundwater that feeds wells and springs. They poison the soil where plants try to grow. Years later, long after the leak has been discovered and the tank replaced, the chemicals remain, a toxic legacy beneath our feet. Even the air we breathe is affected. When corrosion weakens industrial equipment, leaks release volatile organic compounds, particulate matter, and other pollutants into the atmosphere. These substances contribute to smog, acid rain, and respiratory illnesses in human populations. Wildlife suffers too. Birds breathe contaminated air. Animals drink from polluted streams. Plants absorb toxins through their roots. The web of life is interconnected, and corrosion's effects ripple outward in ways we're only beginning to understand. And then there are the storage tanks, countless containers holding the fuels and chemicals our society depends upon. Underground and above-ground storage tanks, such as those used for fuels and chemicals, suffer heavily from corrosion, with direct corrosion costs for these tanks alone estimated at about $7 billion per year in the United States. $7 billion. Every single year, just for storage tanks. Think of the scale this represents. Gasoline stations have underground tanks. Farms have tanks for diesel and agricultural chemicals. Factories have tanks for industrial solvents. Homes heat with oil stored in basement tanks. Military bases, airports, hospitals. Everywhere you look, there are tanks. And every single one of these tanks is vulnerable. Underground tanks face moisture, soil chemistry, and stray electrical currents. Above-ground tanks endure weather, temperature swings, and atmospheric exposure. The metal walls of these containers are under constant assault. The $7 billion figure includes inspection costs, monitoring systems, protective coatings, cathodic protection installations, repairs, and replacements. It includes the cost of environmental remediation when tanks fail and leak. It includes regulatory compliance and emergency response. But even $7 billion doesn't capture the full picture. That's just the direct, measurable costs. It doesn't account for business interruptions when a tank fails, or the long-term environmental damage from contaminated sites, or the health effects on nearby populations. These tanks are absolutely critical to our infrastructure, and yet they are silently deteriorating, year after year, requiring constant vigilance and investment just to keep them functional. Speaking of infrastructure, corrosion in critical infrastructure, bridges, pipelines, tanks, and buildings, can lead not only to massive repair bills, but also to leaks, spills, and structural failures if not detected and controlled early. This is the fundamental challenge we face. Corrosion is progressive. It starts small and grows. And if we don't catch it early, the consequences multiply exponentially. A small rust spot on a bridge beam might require only some cleaning and a fresh coat of protective paint if caught early. But if that rust is allowed to progress, it eats deeper into the metal. The beam weakens. Cracks develop. Eventually, the beam may need to be replaced entirely, a vastly more expensive and disruptive repair. The same principle applies to pipelines carrying water, gas, or oil across thousands of miles. A tiny pinhole leak detected early might be patched quickly and cheaply. But if that leak goes unnoticed, it enlarges. Pressure drops. Flow is disrupted. The escaping substance damages surrounding areas. By the time someone notices, the simple fix has become a major excavation and pipeline replacement project. Early detection is everything. Modern infrastructure monitoring uses ultrasonic testing, electromagnetic sensors, smart gauges, and even drones equipped with specialized cameras to spot corrosion before it becomes critical. These technologies are improving constantly, giving us better tools in the fight against our invisible enemy. But even with the best monitoring, corrosion finds ways to surprise us. Which brings us to a particularly interesting phenomenon. Vapor corrosion occurs without liquid water, as humid air alone can drive rusting on exposed steel, which is why indoor storage still requires desiccants or protective wraps in humid climates. Many people think of rust as something that requires rain or submersion. They picture a piece of metal left out in a storm, water pooling on its surface. But corrosion is far more subtle than that. Water vapor in the air, moisture you cannot see, is enough to initiate and sustain corrosion. When humidity levels rise above about 60%, water molecules begin to form an invisible film on metal surfaces. This microscopic layer of moisture is all corrosion needs. The water film allows ions to move, enables electrochemical reactions, and provides the medium for rust to form. Steel kept indoors, protected from rain, can still rust away if the air is humid enough. This is why museums use climate control to protect metal artifacts. Why electronics manufacturers store sensitive components in dry rooms. Why naval equipment requires special protection, even when stored in supposedly dry hangars near the coast. In humid climates, the battle against vapor corrosion is constant. Desiccants, substances that absorb moisture from the air, are placed inside storage containers. Machinery is wrapped in special vapor barrier films. Dehumidifiers run continuously in warehouses. All of this effort and expense just to keep the air dry enough to slow down corrosion. And humidity isn't uniform. The corrosion rate varies dramatically depending on where you are. Atmospheric corrosion varies by zone. Rural areas see slow rust, industrial zones corrode several times faster, and marine coasts experience the most aggressive attack from salt spray. Location, it turns out, is everything when it comes to corrosion rates. In a rural area, far from industry and ocean, the air is relatively clean. Corrosion still happens, of course. Oxygen and moisture are everywhere. But without additional aggressive factors, the process is slow. A steel structure in rural farmland might last decades with minimal protection. Move that same structure to an industrial zone, and everything changes. The air contains sulfur dioxide from burning fossil fuels. It carries nitrogen oxides from vehicle emissions. Industrial processes release various chemicals into the atmosphere. All of these substances accelerate corrosion. Acids form when these pollutants mix with moisture. The corrosion rate can be 3, 4, 5 times faster than in rural areas. But the most aggressive environment of all is the marine coast. Here, salt spray is the villain. Every wave that crashes against the shore sends tiny droplets of salt water into the air. The wind carries this salt spray inland, coating everything within miles of the ocean. Salt is hygroscopic. It attracts and holds moisture. Even when the air seems dry, salt deposits on metal surfaces remain damp. And salt water is far more conductive than fresh water, allowing corrosion reactions to proceed much more quickly. Coastal infrastructure faces a brutal challenge. Bridges over bays, port facilities, beachside buildings. All of these require extensive protective measures and frequent maintenance. The same structure that would last 50 years inland might need major corrosion repairs after just 10 years on the coast. And salt's corrosive effects aren't limited to natural coastal environments. We bring the salt inland ourselves. Salt-accelerated atmospheric corrosion on highways causes dramatically more vehicle underbody rust in winter road salt regions than in dry inland areas. If you've ever lived in a northern state that salts its roads each winter, you've likely seen this effect firsthand. Cars that are just 5 or 6 years old with rust eating through their frames, exhaust systems hanging loose, body panels perforated with holes. Road salt is tremendously effective at melting ice and improving winter driving safety. But it's also tremendously corrosive. When vehicles drive through salted slush, the salt spray coats the entire undercarriage. It gets into every crevice, every joint, every hidden surface where metal meets metal. Even after the road is clear and dry, the salt remains. It continues its corrosive work through humidity and morning dew. Wash your car, and new salt coats it on the next drive. The cycle repeats throughout the winter, month after month. Compare this to a vehicle in Arizona or Southern California, where roads are never salted. That vehicle's undercarriage might remain pristine for decades. The difference is startling. 2 identical cars use the same amount, but one exposed to road salt and one not. After 10 years, they hardly seem like the same model. The automotive industry has responded with better rust protection, galvanized steel, improved undercoatings, cavity wax injections. But the battle continues, because salt is relentless. And this brings us to the final thought for this segment, the overarching truth that encompasses everything we've discussed. The mystery of corrosion is that it is everywhere, often unseen, quietly reshaping the modern world. As you drift towards sleep tonight, consider this. Corrosion is happening right now, in the pipes beneath your street, in the frame of the car parked outside, in the supports of bridges you crossed today, in industrial facilities miles away, in the hull of a ship at sea, and the wing of an aircraft between flights. It never stops. Not for a moment. Every second, millions of iron atoms are oxidizing, losing electrons, transforming from strong metal into flaky rust. The process is occurring on an atomic scale, invisible to the naked eye, until suddenly it isn't. Until the rust blooms, the pipe leaks, the beam weakens, the structure fails. And yet, despite its ubiquity and its power, corrosion remains something of a mystery to most people. It's a problem for engineers and maintenance crews, not something the average person thinks about. We take for granted that our infrastructure will hold, that our water is safe, that our vehicles will start and our buildings will stand. Corrosion is quietly reshaping our world in ways both large and small. It's determining which bridges get closed and which remain open. It's influencing where industries locate their facilities. It's driving innovation in materials science and protective coatings. It's consuming billions of dollars and countless hours of labor in an endless effort to slow its advance. The modern world exists in a constant state of maintenance and repair, much of it necessitated by corrosion. We are always running to stay in place, always patching and protecting and replacing, always fighting against the natural tendency of refined metals to return to their oxidized, ore-like state. And so the mystery deepens. How do we build a lasting civilization on a foundation that is always, inevitably, slowly dissolving? How do we maintain the systems we depend upon when the very materials they're made from are under constant attack? These are the questions that will guide us through the hours ahead. Rest now. Let your mind drift. The invisible enemy all around us will wait, patiently, as it always does, while we explore its secrets together. Welcome back. Let your breathing slow. Relax your shoulders. We continue our journey into the world of corrosion. And now we turn our attention to something that affects every person, every business, every government on Earth. Tonight, we explore the enormous cost of rust. Numbers can be abstract. When we hear billions or trillions, our minds sometimes struggle to grasp the scale. But these aren't just numbers. They represent real resources, real labor, real limitations on what our society can accomplish. So let us begin with a figure that should, perhaps, take your breath away. The United States spends hundreds of billions of dollars each year dealing with corrosion across infrastructure, vehicles, pipelines, and industry, estimated at about 3 to 4% of United States gross domestic product. 3 to 4% of everything, of the entire economic output of the nation. Think about what that means. The The gross domestic product represents every good produced, every service rendered, every transaction completed in a year. It's the sum total of American economic activity. And somewhere between 3 and 4% of all that effort, all that value, goes toward dealing with corrosion. To put it another way, for every $100 of economic activity, $3 or $4 are consumed by the need to prevent, manage, repair, or replace things damaged by rust. This isn't money spent building new things or improving our quality of life. It's money spent just to maintain what we already have, just to keep things from falling apart. This happens in every sector. Transportation departments repair corroded bridges and highways. Utilities replace aging water and gas pipes. Industries shut down equipment for corrosion maintenance. Vehicle owners pay for rust repairs. Homeowners replace corroded water heaters and HVAC systems. The costs are diffuse, spread across millions of individual decisions and repairs, but they add up to a staggering total. And when we try to pin down a specific figure, to put a dollar amount on this invisible enemy, one widely cited figure puts the yearly cost of rust in the United States at roughly $400 to $440 billion. Let that number settle in your mind. $400 billion. Every year, just in the United States alone. To give this some perspective, $400 billion is more than the entire economic output of many countries. It's comparable to the gross domestic product of nations like Norway or Austria or Singapore. Except instead of building economies, we're spending it on corrosion. What could we do with $400 billion? We could renovate every school in America. We could provide universal broadband access to rural areas. We could fund medical research, expand public transportation, invest in renewable energy infrastructure. But instead, a significant portion of that money goes toward fighting rust. $400 billion spread across a year means more than $1 billion every single day. While you sleep tonight, over $1 billion will be spent somewhere in America dealing with corrosion. Tomorrow, another billion. The day after that, another billion. Relentlessly, endlessly. The figure includes direct costs like materials and labor for repairs. It includes the cost of protective coatings and monitoring systems. It includes replacement of corroded infrastructure. But as staggering as this number is, it's actually just the American portion of a much larger global problem. The global cost of corrosion is estimated at about $2.5 trillion per year, roughly 3.4% of global gross domestic product. $2.5 trillion worldwide, every year. This is a number almost too large to comprehend. Written out, it's $2,500,000 million. The combined wealth of the world's richest individuals, all of them together, doesn't approach this annual figure. The entire global military spending, for every nation on Earth combined, is less than this annual corrosion cost. And just like in the United States, this represents 3 to 4% of everything humanity produces. All the agriculture, all the manufacturing, all the services, all the technology, take 3 to 4% of it, and it goes toward managing corrosion, not toward growth, not toward innovation, toward maintenance and repair and replacement. Different regions face different challenges. Coastal nations with humid climates spend proportionally more. Industrial nations with aging infrastructure spend more. Developing nations with fewer resources for preventive maintenance may face higher failure rates and more catastrophic costs when things go wrong. But no nation escapes. From the frozen pipelines of Siberia to the salt-sprayed bridges of the Caribbean, from the humid industrial zones of Southeast Asia to the desert installations of the Middle East, corrosion is extracting its toll. Yet even $2.5 trillion may be understating the true cost. Because that figure, enormous as it is, only captures direct expenses. If indirect costs like lost productivity and downtime are included, corrosion costs may exceed 6% of global gross domestic product. 6%, double the direct cost estimate. This is where the true economic impact of corrosion reveals itself. Consider what happens when a pipeline corrodes and fails. The direct cost is clear: excavation, pipe replacement, soil remediation. Those expenses are tallied and included in that $2.5 trillion figure. But what about everything else? The factory that relied on that pipeline sits idle while repairs are made. Workers are sent home. Production schedules slip. Delivery commitments are missed. Customers grow frustrated and perhaps switch suppliers. The factory loses revenue, far exceeding the cost of the pipeline repair itself. Or consider a corroded bridge that must be closed for emergency repairs. The direct cost is the repair work, but commuters must detour, adding hours to their daily travel. Delivery trucks take longer routes, burning more fuel. Emergency vehicles face delays reaching people in need. Businesses near the closed bridge lose foot traffic. The economic ripple effects spread outward like waves from a stone dropped in still water. These indirect costs are harder to measure. They don't appear on repair invoices. They're diffused across countless individuals and businesses. But they're very real, and they add up to potentially another 2 to 3% of global economic output. When you include lost productivity, production delays, missed opportunities, reduced efficiency, and all the cascading consequences of corrosion failures, the true cost may approach 6% of everything humanity produces. That's 6 out of every $100 of global economic activity consumed by corrosion and its consequences. And certain industries face even heavier burdens. In energy and petrochemical industries, corrosion can account for up to about 3% of a country's gross national product. This is remarkable when you consider that we're talking about a single industrial sector being responsible for 3% of an entire nation's economic output, just in corrosion costs. Energy infrastructure is particularly vulnerable. Oil refineries process crude oil at high temperatures and pressures, in the presence of sulfur compounds and other corrosive agents. Natural gas processing facilities handle gases that may contain moisture, carbon dioxide, and hydrogen sulfide, all highly corrosive. Power plants, whether fossil fuel or nuclear, operate under extreme conditions that accelerate corrosion. Petrochemical facilities are essentially vast networks of pipes, vessels, and tanks, all containing aggressive chemicals at various temperatures and pressures. The materials used must resist not just atmospheric corrosion, but chemical attack from the substances they contain. Despite using corrosion-resistant alloys and protective coatings, failures still occur with regularity. The 3% figure reflects both the direct costs of managing corrosion in these facilities and the enormous economic impact when failures occur. A refinery shutdown for corrosion repairs might cost millions per day in lost production. A pipeline failure might disrupt fuel supplies to entire regions. The stakes are immense, and the failure rate in these industries tells its own story. Corrosion-related failures in oil and gas equipment have been estimated to cause about 30% of equipment failures in some studies. 30%. Nearly 1 in 3 failures traced back to corrosion. This statistic is both alarming and revealing. Despite decades of corrosion research, despite sophisticated monitoring systems, despite the use of specialized materials and protective measures, corrosion still defeats us nearly a third of the time. Some of these failures are preventable. They result from delayed maintenance, inadequate inspection, or failure to apply known best practices. But many occur despite our best efforts. Corrosion finds weak points. It exploits gaps in protective coatings. It accelerates in unexpected ways when multiple factors combine. In oil and gas operations, equipment operates under punishing conditions. Offshore platforms face salt spray and humidity. Downhole equipment in oil wells encounters high pressures, high temperatures, and corrosive formation fluids. Pipelines span thousands of miles through varying soil conditions. Storage tanks hold products that may themselves be corrosive. When equipment fails in these settings, the consequences can be severe. Production losses cost money. Environmental spills require cleanup. Worker safety is threatened. And in the worst cases, failures can lead to explosions and fires. The 30% figure represents an ongoing challenge for the industry. It's not that corrosion isn't being taken seriously. It is. Billions are spent on corrosion management in oil and gas operations. But the enemy is persistent and adaptable. When we look across all sectors of the economy, the costs spread out in sobering patterns. Industry breakdowns show tens of billions lost annually across infrastructure, manufacturing, transportation, government, and utilities. The corrosion burden doesn't fall on any single sector. It affects everything. Infrastructure, our roads, bridges, tunnels, dams, and public buildings, loses tens of billions to corrosion each year. Steel reinforcement in concrete corrodes, weakening structures decades before their intended lifespan ends. Bridge decks deteriorate under the assault of weather and road salt. Water and sewer systems corrode from within, requiring constant replacement. Manufacturing facilities face their own corrosion challenges. Production equipment corrodes. Buildings corrode. Material handling systems corrode. Every factory, every plant, every production facility must budget for corrosion control and repair. Transportation is hit particularly hard. Vehicles rust. Ships corrode in seawater. Aircraft face corrosion from humidity and de-icing fluids. Railways sea track and rolling stock deteriorate. Ports and airports require constant maintenance against corrosion. Government bears enormous corrosion costs. Military equipment faces some of the most aggressive corrosion environments imaginable. Ships at sea, aircraft exposed to salt air, vehicles operating in desert sand and coastal humidity. Government buildings age and corrode. Public infrastructure requires maintenance. Utilities, electricity, water, gas, telecommunications, all depend on extensive networks of equipment exposed to the environment. Power lines corrode. Water towers rust. Gas pipelines deteriorate. Cell towers and telephone poles face corrosion from weather and pollution. Tens of billions in each sector. Add them up, and you get those hundreds of billions of dollars spent annually in the United States alone. The costs are everywhere, touching every aspect of modern life. And within the broad category of manufacturing, certain industries face exceptional corrosion challenges. Within production and manufacturing, industries like petroleum refining, chemicals, food processing, and agriculture lose billions each year to corrosion. Each of these industries has unique corrosion challenges. Petroleum refining handles crude oil and its derivatives, which contain sulfur compounds that form corrosive acids. High temperatures and pressures accelerate corrosion. Refineries use specialized steels and alloys, apply protective coatings, and monitor constantly, yet still face billions in annual corrosion costs. Chemical manufacturing deals with acids, bases, solvents, and reactive compounds. Vessels and pipes must resist chemical attack, while also withstanding temperature and pressure stresses. Even tiny amounts of corrosion can contaminate products, making quality control another concern beyond just structural integrity. Food processing might seem benign, but it's surprisingly corrosive. Many foods are acidic. Cleaning involves harsh chemicals and hot water. Sanitizing requires aggressive disinfectants. Equipment must be made of expensive stainless steels and still requires frequent replacement. Agriculture involves fertilizers, which are often salt-based and highly corrosive. Pesticides and herbicides attack metal equipment. Moisture from rain and irrigation accelerates corrosion. Farm machinery, storage facilities, and irrigation systems all face significant corrosion challenges in environments that are humid, dusty, and chemically aggressive. Billions of dollars across these industries. Billions that represent not just money but opportunity cost. Resources that could have gone toward innovation, toward improving products, toward expanding operations. Instead, they go toward replacing corroded equipment and maintaining aging infrastructure. And here's perhaps the most frustrating aspect of this enormous economic burden. Studies suggest existing corrosion control practices could reduce global costs by 15 to 35%. 15 to 35%. We already know how to prevent much of this damage. The knowledge exists. The technologies exist. The practices exist. But they aren't being applied universally or consistently. Think about what a 15 to 35% reduction would mean. Applied to that $2.5 trillion global cost, we're talking about savings of $375 billion to $875 billion per year. Nearly $1 trillion at the high end, just from using techniques and technologies we already have. Why isn't this happening? The reasons are complex and varied. Sometimes it's a matter of upfront cost. Protective measures require investment now for savings later, and decision-makers may prioritize short-term budgets over long-term economics. Sometimes it's lack of awareness. Not everyone understands the importance of corrosion control or knows what practices to implement. Sometimes it's institutional inertia. Changing established procedures is difficult even when better methods exist. There's also the challenge of split incentives. The person who builds a structure may not be the person who maintains it. A contractor might choose cheaper materials to win a bid, and years later, a different organization bears the cost of accelerated corrosion. A property developer might skimp on corrosion protection, and future owners face the consequences. But the 15 to 35% figure tells us something important and hopeful. Significant improvement is possible. We're not fighting an unwinnable battle. We have effective weapons. We just need to deploy them more widely and consistently. Better corrosion management is considered one of the lowest cost ways to improve infrastructure reliability worldwide. This is the silver lining in our exploration of corrosion costs. Yes, the problem is enormous. Yes, the expenses are staggering. But the solutions are often surprisingly affordable when compared to the costs of failure. Protective coatings are relatively inexpensive compared to structural replacement. Cathodic protection systems require modest investment, but can extend infrastructure life by decades. Regular inspections cost far less than emergency repairs. Proper material selection during initial construction adds only marginally to project costs, while dramatically reducing lifetime expenses. The return on investment for good corrosion management is exceptional. Spend $1,000 on protective coating, save tens of thousands on repairs. Spend $1 million on a cathodic protection system, save tens of millions in pipeline replacement. The economics are compelling, and infrastructure reliability is worth far more than just avoided repair costs. Reliable infrastructure enables economic activity. It provides predictability that businesses depend on. It keeps supply chains functioning. It allows cities to grow and thrive. The broader economic benefits of reliable infrastructure far exceed the direct costs saved. This is why corrosion management is receiving increasing attention from governments, industry groups, and infrastructure owners worldwide. The recognition is growing that corrosion isn't just a technical problem for engineers to solve. It's an economic and policy challenge that affects national competitiveness and quality of life. As you drift toward deeper rest now, consider this. Somewhere tonight, engineers are inspecting a bridge for signs of corrosion. Maintenance crews are applying protective coatings to pipeline sections. Researchers are testing new corrosion-resistant alloys. Plant managers are scheduling equipment replacements before failures occur. These countless individual actions, multiplied across industries and nations, are the ongoing response to the enormous cost of rust. It's a battle fought every day, everywhere, often unseen but economically crucial. The price tag is staggering, but the cost of inaction would be far higher. Rest now. Let these thoughts settle gently in your mind like sediment drifting down through still water. The numbers are large, but they represent something fundamentally simple: the constant need to maintain and protect the physical infrastructure of civilization against the patient, inexorable chemistry of corrosion. The mystery continues: how something as simple as rust can cost so much, affect so many, and yet remains so often overlooked in our daily lives. Sleep on these thoughts, and when we return, we'll explore how corrosion works at its most fundamental level, the chemistry that makes all of this possible. Breathe deeply, let your mind settle. We now turn back the pages of time, traveling through millennia to explore a fascinating question. When did humanity first encounter corrosion? When did our ancestors first notice that the metals they worked with such care could slowly deteriorate and fade away? Tonight, we explore when humans first met corrosion. Imagine, if you will, the ancient world. Picture a time before cities, before written language, before agriculture even. Early humans are discovering that certain stones, when struck, reveal something extraordinary inside: metal. Shiny, malleable, and utterly unlike the rock that contained it. Early human civilizations used mostly gold, copper, and silver, which occur in relatively unreactive native form in nature. This is crucial to understanding why corrosion wasn't initially a major concern for our ancestors. These first metals, the metals of the ancient world, were chosen by nature as much as by humans. Gold is remarkable for many reasons, but perhaps most remarkable is its stability. Native gold, found in streams and exposed rock faces, looks much the same after thousands of years as it did when first formed. A gold nugget buried in soil for centuries emerges still gleaming. This is because gold barely corrodes at all under normal conditions. Its chemical inertness is exceptional. Copper does corrode, forming that distinctive green patina we see on old bronze statues and copper roofs. But copper's corrosion is slow and, in many ways, protective. The patina layer that forms actually shields the underlying metal from further attack. Ancient copper objects survive in recognizable form after thousands of years. Silver tarnishes, turning black from reaction with sulfur compounds in the air. But again, this is a slow process, and the tarnish layer is thin. Ancient silver coins and jewelry, though darkened, remain intact and functional after millennia. So for thousands of years, as humans developed metallurgy, learned to smelt and cast and forge these metals, corrosion was not the pressing problem it would later become. Yes, silver tarnished and copper turned green, but these changes were aesthetic more than structural. Objects remained usable. The metals weren't failing catastrophically or dissolving away to nothing. This allowed ancient civilizations to create lasting monuments. Gold death masks in Egyptian tombs remain pristine after 35 centuries. Bronze bells cast in ancient China still ring clear after 2,000 years. Roman copper plumbing, buried for millennia, is excavated still intact. But then, everything changed. Large-scale corrosion only became a serious problem once iron was widely adopted. Iron transformed human civilization. It was stronger than bronze. It could be hardened into steel. And crucially, it was far more abundant than copper or tin. Iron ore exists in vast quantities across the world. The Iron Age, beginning around 1200 BCE in the Near East and spreading gradually across Europe and Asia, represented a revolution in human capability. Iron tools were sharper and more durable than bronze. Iron weapons gave military advantages to those who possessed them. Iron enabled new forms of agriculture, construction, and manufacturing. But iron came with a curse. Unlike gold, copper, and silver, iron is desperately eager to corrode. Left exposed to air and moisture, iron doesn't form a protective patina. It forms rust, flaky, porous, and constantly growing deeper into the metal. For the first time, humans confronted metals that could simply disappear. An iron tool left outside through a rainy season might emerge barely functional, its surface eaten away. Iron weapons had to be carefully maintained with oil to prevent rusting. Iron structures required constant attention. Iron's strong tendency to oxidize forced societies to confront decay in tools, weapons, and structures. This wasn't just an inconvenience. It was a fundamental challenge to civilization building. How do you create lasting infrastructure with a material that wants to return to rust? Ancient societies developed practical responses. Oil and grease protected iron surfaces. Some cultures discovered that certain treatments, like the traditional Japanese technique of coating iron in urushi lacquer, could slow corrosion dramatically. The famous Iron Pillar of Delhi, erected around 400 CE and still standing relatively rust-free today, was made from remarkably pure iron that resists corrosion better than modern steel. But these were empirical discoveries, practical solutions developed through trial and error. No one understood why iron corroded. No one knew the fundamental chemistry behind rust. For thousands of years, corrosion remained a mystery. Something that happened, something to be dealt with, but not something that could be explained. This began to change as chemistry emerged as a science in the 18th century. In 1788, Austin observed that water in contact with iron becomes more alkaline over time. This was a small observation, easily overlooked, but it hinted at something important. Something was changing in the water. Some chemical process was occurring. Austin likely noticed this while conducting experiments with iron vessels containing water. Perhaps he was using litmus or some other pH indicator available at the time. The water's increasing alkalinity suggested that a reaction was taking place, that iron wasn't simply being eaten away, but was participating in a chemical exchange with its environment. This observation planted a seed. If water chemistry changed in the presence of corroding iron, then corrosion wasn't just physical degradation. It was a chemical transformation. The iron was doing something to the water, and the water was doing something to the iron. But it would take several more decades before someone proposed a comprehensive theory of what was actually happening. In 1819, Louis Jacques Thenard proposed that corrosion should be understood as an electrochemical process. Thenard was a distinguished French chemist who had already made important contributions to chemistry, including the discovery of hydrogen peroxide. His proposal regarding corrosion was revolutionary. Electrochemistry was a relatively new field at the time. The voltaic pile, the first true battery, had been invented by Alessandro Volta only in 1800. The connection between electricity and chemistry was just beginning to be explored. The idea that chemical reactions could generate electrical current, and that electrical current could drive chemical reactions, was still novel. Thenard proposed that corrosion involved similar electrochemical processes. That corroding metal was, in essence, acting as a battery. That electrons were being transferred. That oxidation and reduction were occurring simultaneously at different locations on the metal surface. This was a profound insight. It meant corrosion wasn't simply iron reacting with oxygen in some vague, general way. It was a specific electrochemical process with anodes and cathodes, with electron flow, with distinct half reactions that could be studied and potentially controlled. Thenard's proposal opened the door to scientific understanding of corrosion. But the door was only beginning to crack open. Many more observations and insights would be needed. In 1829, Hall showed that iron does not rust without oxygen. This might seem obvious to us now, but in the early 19th century, it was an important experimental demonstration. Hall likely conducted experiments with iron in sealed vessels, some containing air and others with the air removed or replaced with inert gases. The results were clear. Iron exposed to moisture, but deprived of oxygen, did not rust, or rusted only extremely slowly. Oxygen was essential to the corrosion process. This finding supported Thenard's electrochemical theory. In electrochemical terms, oxygen was serving as the oxidizing agent, accepting electrons at the cathode. Without oxygen, the cathodic reaction couldn't proceed, and corrosion halted. Hall's work also had practical implications. If oxygen could be excluded, corrosion could be prevented. This principle underlies modern techniques like nitrogen purging of storage tanks and oxygen scavenging in boiler water treatment. But iron, as researchers would discover, had more surprises in store. In 1836, Schonbein demonstrated that iron can become passive under certain conditions. Christian Friedrich Schonbein was a German-Swiss chemist who would later become famous for discovering ozone. But his work on iron passivity was equally important for corrosion science. Passivity is a strange and counterintuitive phenomenon. Under certain conditions, iron becomes remarkably resistant to corrosion, even in environments where it should corrode rapidly. It's as if the iron falls asleep, becoming unreactive despite being exposed to corrosive agents. Schonbein found that when iron is immersed in concentrated nitric acid, it initially dissolves, but then suddenly stops. The iron becomes passive. It can then be transferred to other solutions where normal iron would corrode rapidly, and the passive iron remains largely unaffected. This passivity results from the formation of an extremely thin, invisible oxide film on the iron surface. This film, though only nanometers thick, acts as a barrier preventing further reaction. It's a form of corrosion protection that the metal provides for itself under specific conditions. The discovery of passivity was crucial because it showed that corrosion wasn't inevitable. That under the right conditions, even highly reactive metals like iron could resist attack. This opened up possibilities for corrosion control through chemistry. If passivity could be induced and maintained, corrosion could be prevented. Modern stainless steel relies on this principle. The chromium in stainless steel forms a passive film that protects the underlying metal. Much of corrosion engineering involves understanding and maintaining or creating passive conditions. As these experimental observations accumulated, the theoretical framework was also developing. Early work by Humphrey Davy and Michael Faraday linked corrosion directly to electrochemical reactions. These two giants of 19th century science brought their considerable talents to bear on understanding corrosion. Humphrey Davy, in the 1820s, conducted pioneering experiments on the corrosion of copper sheathing on the hulls of naval vessels. The British Royal Navy had sheathed ship hulls in copper to prevent fouling by marine organisms and to protect the wood from shipworms. But the copper corroded, especially near the iron bolts that held it in place. Davy demonstrated that connecting zinc blocks to the copper provided protection. The zinc corroded preferentially, and the copper was preserved. This was the first practical application of what we now call cathodic protection, one of the most important corrosion control techniques. Davy understood this in electrochemical terms. The zinc was more active than copper, creating a galvanic cell where the zinc acted as the anode and the copper as the cathode. Though Davy's zinc protectors created problems on naval vessels by allowing fouling to occur unchecked, his principle was sound and revolutionary. Michael Faraday, Davy's protégé and eventual successor, made fundamental contributions to electrochemistry in the 1830s and 1840s. Faraday's laws of electrolysis quantified the relationship between electric current and chemical change. Though Faraday didn't focus specifically on corrosion, his work provided the mathematical and conceptual foundation for understanding corrosion as an electrochemical process. Together, Davy and Faraday established that corrosion was fundamentally electrical in nature. That understanding corrosion required understanding electron transfer, oxidation-reduction reactions, and the behavior of electrochemical cells. But observations and principles, however brilliant, don't by themselves constitute a complete science. That would require someone to synthesize all the accumulated knowledge into a unified whole. U.R. Evans' work in the early 20th century unified corrosion into a coherent scientific theory. Ulrich Richardson Evans was a British physical chemist who, beginning in the 1920s and continuing through the 1960s, essentially created the modern science of corrosion. Evans brought together all the scattered observations, the empirical findings, the electrochemical principles, and wove them into a comprehensive theory of how corrosion works. His books, particularly The Corrosion and Oxidation of Metals, first published in 1960, became the foundational texts of corrosion science. Evans explained corrosion in terms of local anodic and cathodic sites on metal surfaces. He described how even apparently uniform metal has microscopic variations in composition, stress, and surface condition that create countless tiny electrochemical cells. He explained the roles of oxygen, water, ions, and pH. He connected laboratory observations to real-world corrosion phenomena. Before Evans, corrosion knowledge was fragmented. Practical techniques here, scientific observations there, theoretical principles somewhere else. After Evans, corrosion was a proper scientific discipline with a theoretical framework that could explain observations and predict behavior. Evans also emphasized that corrosion is not one process, but many. Different mechanisms operate in different environments. Uniform corrosion differs from pitting corrosion differs from stress corrosion cracking. Understanding corrosion requires understanding this diversity. The impact of Evans' work cannot be overstated. He trained generations of corrosion scientists. He established corrosion research as a legitimate field. He provided the knowledge base that industry needed to develop better corrosion control practices. And then, in 1938, came a tool that would transform corrosion science from qualitative to quantitative. Pourbet diagrams, introduced in 1938, mapped corrosion behavior as a function of chemistry and potential. Marcel Pourbet was a Belgian chemist who developed these diagrams as part of his doctoral work and continued to refine them throughout his career. A Pourbet diagram is a map. The vertical axis represents electrical potential. The horizontal axis represents pH, the acidity or alkalinity of the solution. And within this map, regions are marked showing where a metal will corrode, where it will remain immune to corrosion, and where it will become passive. The elegance of Pourbet diagrams is that they reduce enormously complex chemistry to a simple visual representation. Look at the diagram, note your pH and potential, and you can immediately see whether corrosion is thermodynamically favorable or not. This doesn't tell you everything, of course. It doesn't tell you how fast corrosion will occur. It doesn't account for every possible chemical species or for kinetic factors that might slow or accelerate reactions. But it provides a fundamental framework for understanding corrosion behavior. Pourbet diagrams are used today in virtually every aspect of corrosion engineering. They guide the selection of materials for specific environments. They inform the design of cathodic protection systems. They help predict the stability of protective films. They are, quite simply, one of the most useful tools in the corrosion engineer's arsenal. As you drift now towards sleep, consider this journey we've taken. From ancient humans working with gold and copper, metals that barely corroded at all, to the challenges of the Iron Age when corrosion became an unavoidable problem. From the first chemical observations in the late 18th century to the gradual assembly of an electrochemical understanding in the 19th century. From Evans' synthesis in the early 20th century to Pourbet's elegant diagrams. Humanity's relationship with corrosion has evolved from simple observation to deep scientific understanding. We've gone from passive acceptance of rust as an inevitable nuisance to active management based on electrochemical principles. And yet, as we've learned in earlier segments, corrosion still costs trillions of dollars per year. Understanding is not the same as controlling. We know how corrosion works, but stopping it remains an endless challenge. Rest now. Let the history settle in your thoughts like layers of sediment accumulating over geological time. Each observation, each insight, each discovery built upon the ones before, gradually revealing the mystery of corrosion. When we return, we'll explore the chemistry itself, the actual mechanisms by which metal transforms into rust, atom by atom, electron by electron. The mystery deepens as we peer into the molecular world where corrosion actually happens. Welcome back. Settle into comfort. Let your muscles release their tension. We've traveled through history, explored the costs, and met the scientists who unraveled the mystery. Now, we descend to the fundamental level. Tonight, we explore how corrosion actually works, the intricate dance of atoms and electrons that transforms solid metal into crumbling oxide. Let's begin with a word we've used many times already, but perhaps haven't fully defined. Rust. What exactly is rust? Rust is specifically the corrosion product of iron and its alloys, forming iron oxides when iron reacts with oxygen and water. This specificity is important. In everyday language, people often use rust to describe any corrosion. We might say aluminum rusts, or zinc rusts, or that rust has appeared on a copper pipe. But technically, scientifically, rust refers only to iron. Rust is iron oxide. More precisely, it's a mixture of several iron oxides and iron oxide hydroxides. The most common forms are hematite, which is ferric oxide with the chemical formula Fe2O3, and magnetite, which is ferrous-ferric oxide with the formula Fe3O4. There's also lepidocrosite and goethite, iron oxide hydroxides with slightly different structures. These iron oxides form when iron reacts with oxygen in the presence of water. The water is crucial. Dry oxygen alone corrodes, iron only very slowly. But add moisture, and the reaction accelerates dramatically. The water acts as a medium allowing ions to move and electrons to transfer. It completes the electrochemical circuit that drives corrosion. Rust has that characteristic reddish-brown color we all recognize. It's flaky and porous, constantly cracking and exposing fresh metal beneath. This is why rust is so destructive. Unlike the protective patterns that form on some metals, rust doesn't protect the underlying iron. It just keeps growing, layer after layer, until the metal is consumed entirely. But what about other metals? They corrode too, don't they? Other metals corrode, but do not technically rust. This is a matter of terminology and chemistry. Aluminum forms aluminum oxide. Copper forms copper carbonate and copper oxide, which we see as that green or brown patina. Zinc forms zinc oxide and zinc carbonate. Silver forms silver sulfide, the black tarnish on old silverware. Each metal has its own characteristic corrosion products, with their own colors, structures, and properties. Aluminum oxide forms a thin, hard, transparent layer that actually protects the metal beneath, which is why aluminum doesn't seem to corrode away despite being a reactive metal. Copper's green patina is also protective, which is why ancient copper objects survive in good condition. But none of these is rust. Rust is iron's special curse, a corrosion product that doesn't protect, that keeps growing, that eventually reduces the strongest steel to powder. The terminology matters because it reflects the chemistry. Different metals corrode by different mechanisms at different rates in different environments. Understanding corrosion requires understanding these specific chemical processes, not treating all metal degradation as identical. So now let's peer deeper. What's actually happening at the surface of corroding metal? What's the mechanism? Corrosion is driven by electrochemistry, with microscopic anodes and cathodes forming on metal surfaces. This is the key insight that transformed corrosion from an observed phenomenon to an understood science. Corrosion is an electrochemical process. It's essentially the same process that happens in a battery, but instead of generating useful electricity, it's destroying metal. Imagine a piece of steel exposed to moist air. The surface seems uniform, but at the microscopic level, it's anything but. There are tiny variations in the metal's composition, perhaps a carbon-rich region here, a slightly different crystal structure there. There are variations in stress, perhaps from bending or welding. There are variations in the surface condition, perhaps a scratch here, a thin oxide layer there. These tiny variations create regions with different electrochemical potentials. Some regions become anodic. These are areas where the metal will preferentially corrode. Other regions become cathodic. These are areas that will be protected, at least initially. When an electrolyte is present, moisture containing dissolved ions, these anodic and cathodic regions become connected electrically. Electrons can flow through the metal from anodes to cathodes. Ions can flow through the electrolyte between these sites. An electrochemical cell forms, and corrosion begins. At the anodic sites, metal atoms are destroyed. At the cathodic sites, a different reaction occurs, usually involving oxygen or hydrogen. And connecting these sites, invisible currents flow, electrons through the metal, ions through the electrolyte. The metal surface becomes a landscape of countless tiny batteries, all operating simultaneously, all consuming the metal grain by grain, atom by atom. What exactly happens at those anodic sites? How does solid metal transform into dissolved ions? In the presence of an electrolyte, metal atoms lose electrons and become ions. This is oxidation in its most literal sense, the loss of electrons. Consider an iron atom at the surface of steel. It's part of the metal's crystal lattice, bonded to neighboring iron atoms by metallic bonds. It's stable, solid, structural. But at an anodic site, conditions favor this atom leaving the metal. The iron atom releases 2 electrons into the metal's conduction band. These electrons are now free to flow through the metal toward cathodic sites. The iron atom, having lost 2 electrons, is no longer neutral. It's now a positively charged ion. Fe superscript 2, ferrous ion. This ferrous ion, being positively charged and no longer bonded to the metal lattice, dissolves into the surrounding electrolyte. It drifts away into the moisture film on the metal's surface, pulled by electrical forces toward negatively charged regions. Where the iron atom once was, there's now a vacancy in the metal lattice. A tiny pit, a small absence, and around this absence, other iron atoms are now exposed and vulnerable. They too may release electrons and dissolve. The pit grows. This happens not once, but billions upon billions of times. Each corroding iron atom leaves behind 2 electrons and creates a dissolved ferrous ion. The metal is being consumed, transformed from solid structure into dissolved ions dispersed in water. Meanwhile, those electrons must go somewhere. They flow through the metal to cathodic sites, where they participate in a different reaction, usually the reduction of oxygen. The oxygen accepts electrons and combines with water to form hydroxide ions. These hydroxide ions drift through the electrolyte and eventually encounter the dissolved iron ions, and together they form the solid rust that we observe. The whole process is a circuit. Metal oxidizes at anodes, releasing electrons. Electrons flow to cathodes. Oxygen reduces at cathodes, accepting those electrons. Ions drift through the electrolyte, eventually precipitating as rust. The circuit continues as long as metal, oxygen, and moisture are all present. And this electrochemical process becomes even more dramatic when 2 different metals are involved. Galvanic corrosion occurs when 2 different metals are electrically connected in an electrolyte. You may have heard the term galvanic before. It comes from Luigi Galvani, an 18th century scientist who studied bioelectricity, and it refers to electricity produced by chemical means. When 2 different metals touch each other in the presence of an electrolyte, they form what's called a galvanic couple. The 2 metals have different electrochemical potentials. One is more active, more eager to corrode, and the other is more noble, less reactive. A classic example is steel screws in an aluminum structure, common in boats and aircraft. Steel and aluminum have different positions in the galvanic series. When they touch in the presence of salt water or even humid air, a powerful electrochemical cell forms. The electrical connection between the 2 metals allows electrons to flow easily from one to the other. The electrolyte provides ionic conductivity, completing the circuit. Current flows, and corrosion accelerates dramatically. The more active metal corrodes faster, while the more noble metal is protected. This is the fundamental principle of galvanic corrosion. In the steel-aluminum example, aluminum is more active. It's more eager to give up electrons and dissolve. So aluminum becomes the anode of this galvanic cell and corrodes rapidly. The steel, being more noble, becomes the cathode. Electrons flow into the steel from the corroding aluminum. At the steel's surface, these electrons reduce oxygen, but the steel itself doesn't corrode. In fact, the steel is protected by this process. The aluminum is sacrificing itself to protect the steel. This same principle is used deliberately in cathodic protection. Zinc blocks attached to ship hulls or steel pipelines corrode preferentially, protecting the steel. Magnesium anodes in water heaters corrode instead of the steel tank. These are intentional galvanic couples designed to control where corrosion occurs. But when galvanic corrosion happens unintentionally, it can be devastating. The aluminum structure can be eaten away rapidly, failing far sooner than expected. Repairs are expensive and sometimes dangerous, especially in critical structures like aircraft. Engineers must carefully consider galvanic effects when selecting materials. If different metals must be used together, they should be as close as possible in the galvanic series to minimize the potential difference. Electrical insulation between the metals can break the circuit. Protective coatings can prevent the electrolyte from completing the circuit. But galvanic effects are just one way that corrosion can accelerate. Environmental conditions play an enormous role. Corrosion accelerates dramatically at higher temperatures, often doubling for every 10 degrees Celsius increase. This is a general rule in chemistry. Reaction rates increase with temperature. The rule of thumb is that many chemical reactions approximately double in rate for every 10 degrees Celsius increase in temperature, and corrosion follows this pattern. Why does temperature have such a powerful effect? Several factors contribute. At higher temperatures, molecules move faster. Reactions occur more quickly. Diffusion rates increase, so oxygen reaches metal surfaces faster, and corrosion products move away faster, exposing fresh metal. Temperature also affects the solubility of gases and salts in water. Warmer water can dissolve less oxygen, which might seem like it would slow corrosion, but the increased reaction kinetics more than compensate. Warmer water also affects the stability of protective films and the aggressiveness of dissolved salts. This temperature effect has huge practical implications. Industrial equipment operating at elevated temperatures faces accelerated corrosion. Boilers, heat exchangers, and high-temperature pipelines require special alloys and protective measures. A system that would last 30 years at room temperature might last only 15 years at 50 degrees Celsius, and perhaps only 7 or 8 years at 80 degrees Celsius. The exponential nature of this temperature effect means that even modest temperature increases can significantly shorten equipment life. This is why cooling systems are so important in industry, not just for process reasons, but also for corrosion control. And temperature isn't the only environmental factor that dramatically affects corrosion rates. Acidic environments cause metals to corrode orders of magnitude faster than neutral water. Orders of magnitude. That means not just twice as fast, or 10 times as fast, but potentially hundreds or thousands of times as fast. Acidity is measured on the pH scale, where pH 7 is neutral, lower numbers are acidic, and higher numbers are alkaline. Each unit on the pH scale represents a 10-fold change in hydrogen ion concentration. So pH 4 is 10 times more acidic than pH 5, and 100 times more acidic than pH 6. In acidic conditions, there's an abundance of hydrogen ions in the solution. These hydrogen ions provide an alternative cathodic reaction. Instead of oxygen reduction being the only cathodic process, hydrogen ions can be reduced directly to hydrogen gas. This means the cathodic reaction can proceed much faster, which in turn allows the anodic metal dissolution to proceed much faster. The result is dramatically accelerated corrosion. Steel that would last decades in neutral water might last months in moderately acidic water, and perhaps only days or hours in strongly acidic conditions. This is why acid rain was such a concern for infrastructure. Even slightly acidic precipitation can accelerate corrosion of bridges, buildings, and monuments. It's why industrial facilities that handle acids must use special corrosion-resistant alloys or plastic-lined equipment. It's why controlling pH is crucial in water treatment and many industrial processes. Some natural environments are acidic. Soils can be acidic, especially in areas with abundant decaying organic matter or where acid-forming minerals are present. Mine drainage is often highly acidic, which is why abandoned mines can corrode steel structures and contaminate streams. On the other hand, alkaline conditions often slow corrosion. Many metals form more stable passive films at higher pH. This is why concrete, which is highly alkaline, provides such good protection to the steel reinforcement embedded within it, at least until the concrete is compromised and acidic conditions develop. But there's another aspect of corrosion that goes beyond mere chemistry and causes very real physical damage. Many corrosion products occupy more volume than the original metal, creating destructive expansion stresses. This is a crucial point often overlooked in thinking about corrosion. Rust isn't just weaker than steel, it's also much bulkier. Iron oxide occupies approximately 6 to 10 times the volume of the iron metal it came from. When steel corrodes, it swells. And because this swelling is constrained by surrounding material, enormous pressures develop. Consider steel reinforcement in concrete. The steel bars are embedded within concrete that has hardened around them. When the steel begins to corrode, rust forms. That rust, occupying far more volume than the original steel, pushes outward against the surrounding concrete. Concrete is strong in compression, but weak in tension. The expanding rust creates tensile stresses that the concrete cannot withstand. Cracks form, radiating outward from the reinforcing bars. These cracks allow more moisture and oxygen to enter, accelerating corrosion further. The cracks widen. Chunks of concrete spool off, exposing more reinforcement. The deterioration cascades. This expansion effect also causes problems in other contexts. Corroding bolts can crack the materials they're fastened to. Rust buildup in tight spaces can jam mechanisms. Corroding pipes can split along their length from internal rust expansion. The volume expansion turns corrosion from merely a weakening process into an actively destructive force. It's not enough that the metal is being consumed. The very products of that consumption are tearing apart the surrounding structure. This is why surface corrosion is often less damaging than crevice corrosion or corrosion in confined spaces. Surface rust can flake away, falling harmlessly to the ground. But rust forming in a tight space has nowhere to go, and the pressures that develop can be enormous, potentially thousands of pounds per square inch in extreme cases. As we bring this segment to a close, consider one final thought about the nature of corrosion. Corrosion is not just chemistry. It is a slow electrical machine eating metals from the inside out. This metaphor captures something essential about corrosion that pure chemistry misses. A machine has parts that work together. A machine has flows of materials, of energy, of information. A machine does work. A machine can be efficient or inefficient. A machine can be controlled or can run wild. Corrosion is all of these things. It has parts, anodes, cathodes, electrolyte, electrical connection. It has flows, electrons through metal, ions through solution, oxygen diffusing to the surface, corrosion products precipitating or dissolving away. It does work, specifically, the destructive work of breaking metallic bonds and dismantling structures. It has efficiency, sometimes slow, sometimes terrifyingly fast. And it can be controlled, or it can run unchecked. The electrical nature is what makes corrosion so insidious. If it were purely chemical, metal plus oxygen equals oxide, it would be simpler to prevent. Just exclude oxygen, and corrosion stops. But because it's electrochemical, because it involves the flow of electrons through the metal itself, and ions through surface moisture, it can proceed even in surprising circumstances. Corrosion can proceed underground where oxygen is scarce, because the cathode can be located somewhere else, perhaps at the surface. Corrosion can proceed on painted steel, because tiny defects in the paint allow the electrochemical circuit to complete. Corrosion can proceed inside sealed systems, because moisture and ions trapped inside provide the electrolyte. The machine analogy also helps us understand corrosion control. To stop a machine, you remove a critical component or interrupt a critical flow. To stop corrosion, we do the same. We might apply a coating to break the electrolyte connection. We might apply cathodic protection to force electrons in the wrong direction, making the entire structure cathodic. We might use inhibitors that poison the electrochemical reactions. We might select materials that don't form effective galvanic couples. Every corrosion control strategy is fundamentally about disrupting this electrochemical machine, breaking the circuit, stopping the flows, preventing the reactions. As you drift now toward deeper rest, picture that corroding metal surface. Imagine the microscopic landscape of anodes and cathodes. Visualize electrons flowing through the crystalline metal lattice like rivers of electricity. See ions drifting through the thin film of moisture. Watch as ion atoms, one by one, release their electrons and dissolve away into nothingness, leaving behind only rust. It's happening right now, everywhere, on every exposed metal surface where moisture and oxygen meet. The slow electrical machine never stops running. Atom by atom, electron by electron, it continues its patient work of reclaiming refined metals and returning them to their oxidized, ore-like state. The mystery of corrosion reveals itself not as a simple chemical reaction, but as a complex electrochemical process. A machine of sorts, running on the potential energy stored in refined metal, consuming that metal to power its own operation, spreading wherever conditions allow. Rest now, let your breathing slow, Let these thoughts of flowing electrons and dissolving atoms drift through your consciousness like morning mist. When we return, we'll explore the many faces of corrosion, the different types, the different mechanisms, the surprising variety of ways that metal can fail. Sleep well. The machine runs on, patient and inexorable, but for now you can rest. Welcome back. Breathe slowly. Let yourself sink deeper into relaxation. We've explored the fundamental mechanisms of corrosion, the electrochemical machine that consumes metal atom by atom. But corrosion is not a single, uniform process. It wears many masks, attacks in many ways, and surprises even experienced engineers with its variety and cunning. Tonight, we explore the many faces of attack. Close your eyes and imagine a sheet of steel. How would you expect it to corrode? Most people, if asked, would probably imagine the entire surface gradually thinning, rust forming everywhere equally, the metal slowly disappearing layer by layer. And sometimes, that's exactly what happens. Uniform corrosion thins metal evenly across the surface. This is the simplest, most predictable form of corrosion. The entire exposed surface acts as a collection of countless microscopic anodic and cathodic sites, randomly distributed and constantly shifting. No particular area is favored. The electrochemical attack proceeds at roughly the same rate everywhere. Picture a steel plate in seawater. Over months and years, the surface becomes rougher, covered with rust. If you measure the thickness of the plate, you find it has thinned uniformly. What was once 10 millimeters thick is now 9 millimeters, then 8, then 7. The reduction is even across the entire surface. Uniform corrosion is, in many ways, the most manageable form of corrosion. It's predictable. Engineers can measure the corrosion rate in millimeters per year and calculate how long the metal will last. They can plan replacements before the metal becomes dangerously thin. They can apply protective coatings and predict their effectiveness. In fact, uniform corrosion often appears worse than it is. A heavily rusted surface looks terrible, but if the corrosion is uniform, substantial metal may remain beneath the rust. The structure may still have years of useful life despite its appearance. But uniform corrosion is not the only face corrosion wears. Not by far. And some of the other forms are far more dangerous precisely because they're less obvious. Localized corrosion, like pitting, creates deep holes that can perforate metal unexpectedly. Pitting is insidious. The surface may look relatively intact, perhaps with just small spots of rust here and there. But beneath those innocent-looking spots, deep cavities have formed, eating through the metal like invisible worms boring through wood. Pitting occurs when the protective film on a metal surface breaks down at isolated points. This might happen due to a scratch, inclusion in the metal, a chloride ion attacking the passive film, or various other factors. Once a pit initiates, conditions inside the pit become self-perpetuating and increasingly aggressive. Here's what happens. Inside the developing pit, metal dissolution occurs. This is the anodic reaction. The metal ions released into the solution attract negative ions, particularly chlorides, to maintain electrical neutrality. The concentration of metal chlorides inside the pit increases, and these salts hydrolyze, making the solution inside the pit acidic. Meanwhile, outside the pit on the surrounding surface, the cathodic reaction occurs, typically oxygen reduction. This consumes hydrogen ions and makes the external solution slightly alkaline. The pit interior becomes a harsh, acidic, chloride-rich environment, while the exterior remains relatively benign. The geometry of the pit makes things worse. The small opening restricts the exchange of solution between the pit interior and the external environment. Oxygen cannot easily reach the pit bottom, so the cathodic reaction cannot occur there. The pit bottom remains anodic, continues to corrode, and the pit grows deeper. A pit might be just a millimeter in diameter, but several millimeters deep. From the outside, you see a tiny rust spot, but the pit has nearly perforated the metal. A pipeline under pressure might fail catastrophically from a single deep pit that was never noticed during inspection. This is why pitting is so dangerous. Uniform corrosion gives warning. The metal visibly thins, strength gradually decreases. Inspectors notice the problem. But pitting can perforate a structure with minimal external evidence, causing sudden, unexpected failure. Stainless steels, which are generally corrosion-resistant, are particularly vulnerable to pitting in chloride-containing environments. The passive film that normally protects stainless steel can break down locally in the presence of chlorides, and aggressive pits develop. This is why stainless steel performs beautifully in many environments, but can fail surprisingly quickly in seawater or other chloride-rich conditions. And pitting isn't the only form of localized attack. There's an even more hidden form that occurs in places we often don't think to look. Crevice corrosion thrives in tight gaps where oxygen depletion creates aggressive conditions. A crevice might be the gap under a washer, the overlap of two metal plates, the space beneath a deposit of dirt or marine growth, or the thread of a bolt. Any narrow gap where solution can enter but circulation is restricted becomes a potential site for crevice corrosion. The mechanism is similar to pitting in some ways. Initially, corrosion might proceed uniformly inside and outside the crevice. But oxygen is consumed by corrosion and cannot easily diffuse into the restricted crevice space. The area outside the crevice, with abundant oxygen, becomes cathodic. The oxygen-depleted area inside the crevice becomes increasingly anodic. Metal dissolves inside the crevice, releasing metal ions. Chlorides migrate into the crevice to maintain charge balance. The metal ions hydrolyze, producing acid. The crevice becomes an acidic, oxygen-free, chloride-rich environment. Highly aggressive conditions that drive accelerated corrosion. The metal inside the crevice corrodes rapidly, while the external surfaces remain largely unaffected. Open up a corroded bolted connection, and you might find the bolt shank pristine, but the area under the bolt head severely attacked. Lift off a gasket, and the metal beneath might be rough and deeply corroded while the surrounding areas are smooth. Crevice corrosion is particularly problematic because crevices are often design features. Bolted connections, flanges, gaskets, overlapping plates. These are standard engineering elements, and all create crevices. Eliminating them is often impossible. Prevention requires careful design to minimize crevice geometry, using sealants to fill gaps, selecting more resistant alloys, or ensuring complete drainage so crevices cannot retain liquid. But despite best efforts, crevice corrosion remains a common and troublesome form of attack. Sometimes, though, corrosion doesn't attack the metal grains themselves, but follows a more subtle path through the structure. Intergranular corrosion follows weakened grain boundaries in alloys. Metals are not uniform at the microscopic level. They're composed of countless tiny crystals called grains, each perhaps a few micrometers across. Where these grains meet, at the grain boundaries, the atomic arrangement is less perfect. The grain boundaries have higher energy and different chemical composition than the grain interiors. In some alloys, under certain conditions, the grain boundaries become depleted in elements that provide corrosion resistance, or they become enriched in more reactive phases. When this happens, the grain boundaries corrode preferentially, while the grain interiors remain relatively unaffected. The classic example is sensitization of stainless steel. When stainless steel is heated to temperatures between about 450 and 850 degrees Celsius, which can happen during welding, chromium carbides precipitate at the grain boundaries. This removes chromium from the adjacent areas, creating zones depleted in the chromium that normally protects stainless steel. When the sensitized steel is exposed to corrosive conditions, these chromium-depleted zones along the grain boundaries corrode rapidly. The result is a network of corrosion following every grain boundary, like cracks running through the metal structure. From the surface, intergranular corrosion might not be immediately obvious. The metal might look relatively intact, but the grain boundaries have been eaten away, and the grains are no longer bonded together. The metal has lost its structural integrity. It might literally fall apart, disintegrating into individual grains like sand when stressed. Intergranular corrosion is prevented through proper alloy selection and heat treatment. Low-carbon stainless steels, or stabilized grades that don't form chromium carbides, are used in welded applications. Solution annealing heat treatments can redissolve the carbides and restore corrosion resistance. But if prevention fails and intergranular corrosion develops, the affected metal usually must be replaced. And then there are forms of corrosion that require not just a corrosive environment, but also mechanical stress. Stress corrosion cracking combines tensile stress and corrosion to cause sudden brittle failure. This is one of the most treacherous forms of corrosion because it can cause catastrophic failure of structures that show little visible evidence of damage. Stress corrosion cracking, or SCC, requires three factors to occur simultaneously. First, a susceptible material. Certain alloy and environment combinations are prone to SCC. Second, a corrosive environment specific to that material. For example, chlorides for stainless steel, or caustic solutions for carbon steel. Third, tensile stress, either applied stress or residual stress locked into the material from fabrication. When all three factors are present, cracks initiate and grow through the metal. The cracks typically propagate perpendicular to the tensile stress direction. They grow steadily, sometimes over years, sometimes over just weeks or days, depending on conditions. The frightening aspect of stress corrosion cracking is that it can occur at stress levels far below the material's normal strength. A structure that would safely carry its load indefinitely in air might fail suddenly when exposed to a specific corrosive environment. The failure is brittle, without the ductile deformation that normally warns of overload. Stress corrosion cracking has caused numerous catastrophic failures. Storage tanks have ruptured, pipelines have split, pressure vessels have exploded. In each case, the metal appeared sound, the stress levels were within design limits, but the specific combination of material, environment, and stress created conditions for SCC. Prevention involves breaking at least one leg of the three-legged stool. Use a different alloy, not susceptible to SCC, in that environment. Change the environment to eliminate the corrosive species. Reduce stress through design changes or stress relief heat treatment. If even one factor is eliminated, SCC cannot occur. But SCC isn't the only way stress and corrosion combine to cause problems. Corrosion fatigue accelerates crack growth under cyclic loading. All engineering structures experience cyclic loads to some degree. Bridges vibrate as vehicles pass. Pipelines experience pressure fluctuations. Aircraft components undergo countless load cycles. Offshore platforms sway in waves. Normally, metals can endure enormous numbers of these cycles without failure, a property called fatigue resistance. But in corrosive environments, fatigue life plummets. Corrosion fatigue is the interaction between cyclic mechanical loading and electrochemical corrosion. The combination is far more damaging than either factor alone. Here's what happens. As the metal flexes under cyclic loading, protective films crack. Fresh, reactive metal is exposed. Corrosion attacks these freshly exposed areas, creating tiny surface defects. These defects act as stress concentrators when the next load cycle occurs. Cracks initiate at these corroded spots far more easily than they would on clean metal. As a crack grows, its tip is constantly being stretched open and closed by the cyclic loading. Each opening exposes fresh metal at the crack tip to the corrosive environment. Corrosion attacks preferentially at the highly stressed crack tip. The crack grows faster than it would in either pure fatigue or pure corrosion. The result is that a component's fatigue life in a corrosive environment might be 1/10 or even 1/100th of its fatigue life in air. A shaft that would last for tens of millions of cycles in dry air might fail after just hundreds of thousands of cycles in seawater. This has enormous implications for marine structures, offshore oil platforms, subsea pipelines, and any equipment that experiences both cyclic loading and corrosive conditions. Design must account for dramatically reduced fatigue resistance, requiring heavier construction, more frequent inspection, or protective measures to exclude the corrosive environment. Sometimes, though, corrosion is accelerated not by stress or cracking, but by movement, the movement of fluids across metal surfaces. Erosion corrosion occurs when fast-moving fluids strip away protective films. We've talked about how many metals form protective oxide layers, or passivate, under certain conditions. These films, though microscopically thin, provide crucial protection against continued corrosion. But what happens when flowing liquid or gas physically removes these protective layers? In erosion corrosion, the mechanical action of fluid flow strips away protective films as fast as they can form. The bare, reactive metal beneath is continuously exposed to the corrosive environment. Corrosion proceeds at the maximum possible rate, limited only by how quickly fresh corrosive species can reach the metal surface. High-velocity seawater in pipes is a classic example. Even stainless steel, normally well protected by its passive film, can suffer erosion corrosion if water velocity exceeds certain limits. The passive film is mechanically disrupted, corrosion accelerates, and the pipe wall thins rapidly. Erosion corrosion often creates distinctive patterns. You might see smooth, wave-like grooves following the direction of flow, or horseshoe-shaped pits with the open end facing downstream. These patterns tell a story of fluid flow and mechanical attack. The damage is often concentrated at turbulent areas, at bends, valves, pumps, or anywhere flow changes direction. At impingement points where jets strike surfaces. These are areas of highest velocity and most aggressive mechanical action. Preventing erosion corrosion requires reducing flow velocities, using more resistant materials, or protecting the surface with coatings or cathodic protection. Pipeline designers must carefully consider velocity limits for different materials. Too slow, and sediment settles and causes other problems. Too fast, and erosion corrosion destroys the pipe. And there's an even more violent form of mechanical corrosion interaction. Cavitation corrosion damages surfaces when collapsing vapor bubbles hammer the metal. Cavitation is a phenomenon that occurs in flowing liquids when pressure drops so low that the liquid locally boils, forming vapor bubbles. When these bubbles move to a higher pressure region, they collapse suddenly and violently. The collapse of a cavitation bubble creates an intense, localized shock wave. If this happens near a metal surface, the shock wave hammers the surface with tremendous force. Protective films are destroyed. Surface metal is plastically deformed or even torn away. The damaged area is then attacked by corrosion. The combination of mechanical damage and corrosion creates deep, irregular pits with a rough, torn appearance. Cavitation damage looks aggressive and violent because each bubble collapse is like a microscopic explosion at the metal surface. Cavitation corrosion commonly occurs on ship propellers, pump impellers, hydraulic turbines, and any equipment where high-velocity liquid flow creates low-pressure zones. The distinctive spongy appearance of cavitation damage is unmistakable once you've seen it. Prevention involves careful hydrodynamic design to avoid low-pressure zones where cavitation initiates. Using harder materials or special coatings can improve resistance to the mechanical damage. Ensuring the liquid doesn't contain dissolved air reduces bubble formation. But cavitation is often difficult to completely eliminate in high-performance hydraulic equipment. Not all mechanical action is as violent as cavitation, though. Sometimes, tiny movements cause big problems. Fretting corrosion arises from tiny repeated motions between contacting surfaces. Imagine two metal surfaces pressed together, perhaps a bolt and its hole, or two plates in a riveted joint, or a bearing and its housing. If these surfaces undergo tiny oscillating relative motions, perhaps from vibration, or thermal expansion and contraction, or slight flexing under load, fretting corrosion can occur. The motion is often just a few micrometers, far too small to see. But it's enough. Each tiny movement causes the protective oxide films on both surfaces to wear away. Fresh metal is exposed and immediately oxidizes. The oxide particles, harder than the underlying metal, act as an abrasive, wearing away more material. The surfaces become rough. More wear occurs. More oxide forms. A vicious cycle develops. Fretting damage appears as fine rust-colored or black powder at the interface between parts. When you disassemble the joint, you find the surfaces pitted and grooved, often with a characteristic radial pattern if the motion was rotational. Fretting is particularly troublesome because it occurs in joints that are supposed to be fixed, not moving. Design assumes no relative motion, so no provision is made for lubrication or other protective measures. But in reality, perfect rigidity is impossible. All structures flex slightly. All joints experience some micromotion. And wherever that micromotion occurs, fretting can develop. Prevention involves increasing clamping force to prevent relative motion, using lubricants to prevent metal-to-metal contact, or choosing material combinations less prone to fretting. In critical applications, special coatings or surface treatments may be applied to resist fretting damage. And finally, there's a form of corrosion that doesn't destroy the metal structure so much as it hollows it out, leaving a fragile shell. Selective leaching removes one element from an alloy, leaving a weakened skeleton behind. Alloys are mixtures of two or more metals, combined to achieve desired properties. But in some environments, one element of the alloy corrodes preferentially, dissolving away and leaving the other elements behind. The classic example is dezinsification of brass. Brass is an alloy of copper and zinc. In some water conditions, the zinc preferentially corrodes and dissolves, leaving behind a porous, copper-rich structure. From the outside, the brass looks normal. It still has its gold color and shape, but it has lost most of its strength. The structure is like a sponge, weak and brittle. You might have a brass valve that looks perfectly fine, but when you try to close it, the handle breaks off in your hand. The dezinsified brass has no mechanical strength left. It crumbles like chalk. Similar phenomena occur in other alloys. Graphitic corrosion of cast iron removes the iron, leaving behind graphite and rust that retains the original shape but has no strength. Dealloying of aluminum bronzes removes aluminum. In each case, the result is a structurally compromised component that appears deceptively intact. Selective leaching is particularly dangerous in critical components because there's little external warning. The part looks fine. Dimensions are unchanged. Only detailed examination or testing reveals that the material has been fatally weakened. Prevention involves using alloys resistant to selective leaching in the specific environment, inhibiting the corrosion with water treatment or cathodic protection. For brass, using inhibited brass alloys with additions of arsenic, tin, or antimony can prevent dezinsification. As you drift now, feeling the weight of sleep approaching, consider the sheer variety we've explored. Uniform corrosion spreading evenly across surfaces, pitting drilling deep, invisible holes. Crevice corrosion hiding in gaps and joints. Intergranular attack following grain boundaries like cracks through glass. Stress corrosion cracking combining chemical and mechanical destruction. Corrosion fatigue accelerating crack growth under cycling loads. Erosion corrosion where flowing fluids strip away protection. Cavitation hammering surfaces with collapsing bubbles. Fretting from tiny vibrations. Selective leaching hollowing out alloys. 10 different faces of corrosion. 10 different mechanisms of attack. Each with its own requirements, its own favored conditions, its own distinctive damage pattern. Each requiring different prevention strategies. This diversity is what makes corrosion engineering so challenging. It's not enough to say, this environment is corrosive. You must ask which forms of corrosion might occur. A solution might be mildly corrosive for uniform attack, but highly aggressive for pitting. An alloy might resist uniform corrosion beautifully, but be vulnerable to stress corrosion cracking. The mystery of corrosion reveals itself to have many layers. Beneath the simple observation that metal rusts lies a complex taxonomy of attack mechanisms, each with its own science, its own dangers, its own solutions. Rest now. Let your mind wander through this landscape of corrosion mechanisms. Picture metal surfaces under attack from all these different directions: chemical, mechanical, the interplay of stress and environment, the influence of flow and geometry. When we return, we'll explore where corrosion strikes, the specific environments and industries where these many faces of attack appear most often and cause the greatest damage. Sleep well. The many-faced enemy continues its work. But for now, you can rest in the knowledge that each face can be recognized, understood, and defended against. Welcome back. Let your body relax completely. Release any remaining tension. We've explored the many faces of corrosion, the diverse mechanisms by which metal can fail. But corrosion has more surprises in store. Sometimes, the attack comes from living things. Sometimes, it hides where we cannot see. Tonight, we explore biology and the unexpected, the ways corrosion surprises us when we're not looking. Take a deep breath and consider this. When we think of corrosion, we think of chemistry, electrochemical reactions, oxidation and reduction, the dance of electrons and ions. We imagine lifeless processes, pure chemistry proceeding according to physical laws. But life has a way of interfering with even the most fundamental chemical processes. Microbiologically influenced corrosion occurs when microorganisms accelerate metal attack. This is corrosion with a biological component. Bacteria, fungi, algae, and other microorganisms don't just exist passively on metal surfaces. They actively change the chemistry around them, creating conditions that drive accelerated corrosion. Microorganisms are everywhere. In soil, in water, on surfaces. Anywhere there's moisture and minimal nutrients, microbial life finds a way. And when microorganisms colonize a metal surface, they fundamentally alter the corrosion environment. Different microorganisms affect corrosion in different ways. Sulfate-reducing bacteria, perhaps the most notorious, live in oxygen-free environments and use sulfate as their oxygen source, producing hydrogen sulfide as a waste product. Hydrogen sulfide is highly corrosive to steel, creating severe localized attack. Iron-oxidizing bacteria accelerate the corrosion of iron by catalyzing the oxidation reaction. They essentially act as little biological machines that speed up rust formation, harvesting energy from the process for their own metabolism. Acid-producing bacteria create locally acidic conditions through their metabolic processes. Remember how acidity dramatically accelerates corrosion? These bacteria bring that acidity directly to the metal surface. Even bacteria that don't directly participate in corrosion chemistry can accelerate attack by consuming corrosion inhibitors, degrading protective coatings, or creating differential aeration cells through their metabolic activities. Microbiologically influenced corrosion, often abbreviated MIC, occurs in countless environments. Underground pipelines in soil teeming with bacteria, water systems where biofilms establish, offshore structures in seawater rich with marine microorganisms, cooling towers where warm water provides ideal conditions for microbial growth, even fuel tanks, where certain bacteria can thrive at the water-fuel interface. The damage from MIC can be severe and rapid. Pipelines that should last decades can perforate in just years when aggressive microbial populations establish. The costs run into billions of dollars annually across industries. And the microorganisms don't just float freely in water, occasionally contacting metal. They organize themselves into complex structures. Biofilms trap oxygen and create acidic microenvironments on metal surfaces. A biofilm is a community of microorganisms living within a self-produced matrix of polymers, essentially a slime layer that adheres tenaciously to surfaces. Think of a biofilm as a microscopic city. The bacteria are the inhabitants, and the polymer matrix is the infrastructure holding everything together. Within this structure, microorganisms cooperate, share nutrients, and create a protected environment where they can thrive. On a metal surface, a biofilm creates major problems. The biofilm matrix restricts the diffusion of oxygen, creating oxygen concentration cells. Areas under thick biofilm become depleted of oxygen and turn anodic. Areas at the edges of the biofilm, with better oxygen access, become cathodic. Accelerated localized corrosion develops under the biofilm. Inside the biofilm, metabolic waste products accumulate. The pH can drop significantly as organic acids build up. The chemistry becomes aggressive, far more so than the bulk environment surrounding the biofilm. The biofilm also provides a protected environment for particularly aggressive bacterial species. Sulfate-reducing bacteria, for instance, are anaerobic. They cannot survive in oxygen-rich water. But deep within a biofilm, where oxygen cannot penetrate, they thrive happily, producing their corrosive hydrogen sulfide right at the metal surface. Biofilms are difficult to remove once established. Their polymer matrix protects them from biocides and mechanical cleaning. They adhere so strongly that complete removal often requires aggressive chemical treatment or physical removal of the affected metal surface. And the corrosion damage caused by these microbial communities takes familiar but devastating forms. Microbial corrosion can cause pitting, crevice attack, and cracking. The localized chemistry created by biofilms and bacterial metabolism drives the same types of damage we've discussed before, but often at accelerated rates. Pitting under biofilms can be particularly aggressive. The combination of oxygen depletion, acid production, and sulfide generation creates conditions ideal for deep pit formation. Pits can grow surprisingly quickly, sometimes penetrating millimeters of steel in just months. The biofilm itself acts like a crevice, creating differential aeration. This drives crevice corrosion mechanisms. The areas under the biofilm corrode, while nearby clean surfaces remain relatively unaffected, creating rough, irregular attack patterns. In some cases, the combination of aggressive chemistry and localized corrosion can even contribute to stress corrosion cracking. The pits and crevices created by microbial attack act as stress concentrators, and the locally aggressive chemistry provides the corrosive environment needed for crack initiation and growth. What makes microbial corrosion particularly troublesome is that it occurs even in environments that would otherwise be only mildly corrosive. Clean freshwater might cause very slow, uniform corrosion of steel, but introduce the right bacterial populations, allow biofilms to form, and suddenly aggressive localized attack develops. The environment hasn't changed, but the microenvironment at the metal surface has been transformed by living organisms. But microorganisms aren't the only things that hide corrosion from view. Sometimes, our own protective measures inadvertently create hiding places. Corrosion under insulation hides severe damage beneath thermal coverings. Industrial facilities are full of hot or cold pipes and vessels covered in thermal insulation. This insulation improves energy efficiency and protects workers from temperature extremes. But it also creates an environment where corrosion can thrive unseen. Water is the culprit. Insulation materials can absorb moisture from rain, leaks, condensation, or even atmospheric humidity. Once wet, insulation is difficult to dry. It holds moisture against the metal surface beneath, creating continuously damp conditions ideal for corrosion. The insulation also creates a crevice between itself and the metal, restricting oxygen access and establishing conditions for crevice corrosion. If chlorides are present in the water, perhaps from coastal spray or from the insulation materials themselves, aggressive localized attack can develop. The temperature of the pipe or vessel also matters. If the surface is warm, corrosion often proceeds faster due to increased reaction rates. If the surface is cold and below the dew point of ambient air, condensation forms continuously on the metal surface under the insulation, maintaining wet conditions even if no external water source exists. The problem with corrosion under insulation, often called CUI, is that it's hidden. The pipe looks fine from the outside. The insulation appears intact. But underneath, severe corrosion may be eating away at the pipe wall. By the time anyone notices, perhaps when a leak develops, or during a scheduled inspection when insulation is removed, extensive damage has already occurred. Industries lose enormous sums to CUI. Unexpected shutdowns for repairs, production losses, safety incidents when corroded lines fail. The costs are particularly high because the problem often isn't discovered until it's severe. Prevention requires keeping insulation dry, using corrosion-resistant jacketing, applying protective coatings to the metal before insulation, and conducting regular inspections that actually remove insulation to examine the pipe beneath. But on a facility with thousands of insulated pipes and vessels, comprehensive inspection is daunting and expensive. And insulation isn't the only covering that hides corrosion. Corrosion under deposits forms beneath scale, sand, or marine growth. Any solid material sitting on a metal surface can create conditions for hidden corrosion. The mechanisms are similar to crevice corrosion and corrosion under insulation. The deposit restricts diffusion, creates differential aeration, and concentrates aggressive species. In boilers and heat exchangers, minerals scale deposits from hard water. These deposits insulate the metal from the bulk fluid, allowing localized overheating and creating crevices where aggressive chemistry develops. Under the scale, rapid corrosion can perforate tubes even as the scale-covered surface appears normal. In pipelines carrying water containing sand or sediment, particles settle at low points. Under these accumulations, oxygen is depleted, creating anodic zones. The acidic conditions that develop drive accelerated attack. Pipelines can be perforated from the bottom, where sediment accumulates, while the top of the pipe remains unaffected. On ships and offshore structures, marine organisms attach to submerged surfaces. Barnacles, mussels, algae, and other growth create complex surfaces with countless crevices and deposits. Under this marine growth, aggressive localized corrosion develops, often surprising ship owners who expected the biological coating to somehow protect the metal rather than accelerate its destruction. Even atmospheric deposits can cause problems. Salt deposits from sea spray or pollutants from industrial atmospheres settle on steel structures. When moisture condenses, these deposits dissolve, creating highly concentrated, corrosive solutions right on the metal surface. Under the innocent-looking layer of dust or salt, intensive corrosion proceeds. The pattern emerges. Corrosion loves to hide. Under insulation, under deposits, under biofilms, under any covering that creates a microenvironment different from the bulk conditions. Out of sight, often out of mind, until failure forces attention. But sometimes corrosion doesn't hide under something. It creates its own distinctive, visible patterns in specific locations. Waterline corrosion creates intense attack bands on ship hulls. If you've seen old boats, you've probably noticed a distinct band of heavy corrosion right at the waterline. That zone where the water surface meets the hull as the boat floats. This waterline zone experiences the most aggressive corrosion conditions on the entire hull. It's subject to cyclic wetting and drying as waves wash up and down. It experiences maximum oxygen availability because air is constantly being mixed into the water by wave action. It often accumulates floating debris and organisms, and the mechanical action of waves constantly refreshes the corrosive environment and can damage protective coatings. The combination creates a perfect storm for corrosion. Below the waterline, oxygen is limited and corrosion proceeds relatively slowly. Above the waterline, the surface is mostly dry and atmospheric corrosion is slow. But right at that waterline band, conditions are optimal for rapid attack. On steel ships, the waterline can corrode several times faster than any other area of the hull. Special protective measures are required. Heavy coatings, impressed current cathodic protection, or frequent maintenance and painting. The width of the affected zone depends on wave action and tidal range. In calm waters, it might be just a few inches. On an ocean-going vessel in rough seas, the zone of maximum attack might extend for several feet vertically. This same principle applies to any structure that spans the water-air interface. Piles supporting piers and docks show maximum attack at the waterline. Offshore platform legs corrode most severely in the splash zone. Even rocks at the seashore show maximum erosion at the tidal zone, where wave action is most intense. Sometimes, though, corrosion creates patterns that are intricate and spreading, almost artistic in their complexity. Filiform corrosion spreads thread-like under damaged coatings. This is a specialized form of corrosion that occurs under organic coatings, particularly on aluminum and magnesium alloys, though it can occur on steel as well. Imagine a painted aluminum panel. A small scratch or defect in the paint exposes the metal. Corrosion initiates at this defect, which isn't surprising. But then something unusual happens. The corrosion begins to spread laterally under the intact paint film, creating thread-like filaments radiating outward from the initial defect. These filaments, typically just a fraction of a millimeter wide, but potentially several centimeters long, grow at their advancing head while leaving behind a trail of corrosion product. The paint film lifts slightly, creating a visible worm-like track across the surface. The mechanism involves moisture permeating through the coating and traveling along the metal coating interface. At the advancing head of each filament, oxygen reduction occurs, while behind the head, in the oxygen-depleted region, metal dissolution proceeds. The geometry maintains itself, and the filament extends steadily, day by day, creating complex, branching networks across the surface. Filiform corrosion is usually more of a cosmetic problem than a structural one. The attack is shallow, rarely exceeding a few tens of micrometers deep. But on aircraft skins or automotive panels where appearance matters, filiform corrosion is a significant defect. And the presence of filiform attack indicates that moisture is penetrating the coating, which may herald more serious corrosion elsewhere. Prevention requires high-quality surface preparation before coating, using appropriate primers, and ensuring coating integrity. Once filiform corrosion starts, the only real solution is to remove all affected coating and corroded metal, then recoat properly. And then there's a form of corrosion that literally peels apart certain metals. Exfoliation corrosion peels alloys apart layer by layer. This specialized form of corrosion affects specific aluminum alloys and occurs along planes parallel to the surface. The corrosion product formation causes swelling, which progressively lifts off layers of metal, like pages in a waterlogged book separating. High-strength aluminum alloys used in aircraft structures are particularly susceptible. These alloys are processed by rolling, which creates a grain structure elongated parallel to the rolling direction. The grain boundaries perpendicular to the surface become pathways for corrosion. When exfoliation occurs, corrosion proceeds along these parallel grain boundaries. The voluminous corrosion products create pressure that forces the layers apart. The metal literally delaminates, with thin leaves of metal lifting away from the substrate. The visual appearance is distinctive. The surface develops a scaly, leafy texture as metal layers peel back. The damage can penetrate deeply into the structure, severely reducing strength and leaving voids that can trap moisture and accelerate further corrosion. Exfoliation is prevented by proper alloy selection, avoiding susceptible orientations in critical applications, or ensuring complete protection from moisture exposure. In aircraft, areas prone to exfoliation require frequent inspection and proactive replacement before severe damage develops. But not all corrosion-related damage looks like corrosion at all. Sometimes, corrosion creates conditions that lead to sudden, brittle fracture with no visible rust or pitting. Hydrogen embrittlement makes high-strength steels brittle and prone to sudden fracture. This is a subtle and dangerous phenomenon where hydrogen atoms, produced during corrosion or introduced during processing, diffuse into the steel and accumulate at internal defects and stress concentrations. Hydrogen atoms are tiny and can squeeze between the iron atoms in steel's crystal lattice. They diffuse readily through the metal, especially at elevated temperatures or under stress gradients. When hydrogen accumulates at internal discontinuities like inclusions, grain boundaries, or the tips of cracks, it reduces the cohesive strength of the metal. High-strength steels are particularly susceptible. The same metallurgical features that make them strong, fine grain structure, high dislocation density, alloying elements, also make them vulnerable to hydrogen embrittlement. The stronger the steel, generally the more susceptible it becomes. A hydrogen embrittled part may look perfectly normal. There's no visible corrosion, no obvious defects. But under stress, particularly sustained load, cracks suddenly initiate and propagate with little or no ductile deformation. The failure is brittle and catastrophic, like breaking glass rather than bending metal. Hydrogen embrittlement has caused failures of high-strength bolts, causing flanges to separate and vessels to rupture. It's caused sudden fractures of landing gear components. It's broken drill pipe in oil wells and cracked pressure vessels in chemical plants. The hydrogen can come from various sources. Corrosion reactions produce hydrogen. Welding introduces hydrogen from moisture in electrodes or shielding gas. Electroplating generates hydrogen at the cathode surface. Even acid cleaning operations can drive hydrogen into steel. Prevention involves using lower strength steels when possible, since they're less susceptible. Baking parts after processes that introduce hydrogen can allow the hydrogen to diffuse out before it causes damage. Applying protective coatings prevents corrosion that would generate hydrogen. And careful control of welding and plating processes minimizes hydrogen introduction. As you rest now, settling deeper into relaxation, consider this final thought about hidden and unexpected corrosion. Some of the most dangerous corrosion happens where no one is looking. This is the theme that connects everything we've explored in this segment. Microorganisms creating aggressive conditions in invisible biofilms. Corrosion hiding under insulation, under deposits, under marine growth. Attack concentrating at waterlines and spreading secretly under coatings. Metals delaminating layer by layer. Hydrogen silently infiltrating steel, waiting to cause sudden fracture. These are not the kinds of corrosion you easily spot during a casual walk-through inspection. They require knowing where to look, what to look for, and often they require removing coverings, taking samples, performing specialized testing. This is why so many corrosion failures come as surprises. The structure looked fine yesterday. Inspections showed nothing unusual, but the hidden corrosion was progressing relentlessly, unseen, until the day it suddenly became visible through failure. It's humbling, really. Despite all our knowledge, all our testing methods, all our monitoring systems, corrosion still surprises us. It finds hiding places. It exploits unexpected vulnerabilities. It teams up with biology in ways we're still learning to understand. It causes damage that doesn't look like typical corrosion damage. The enemy is not just patient and ubiquitous. It's also cunning, finding ways to proceed unnoticed until it's too late. Rest now. Let your mind drift through the hidden places where corrosion works. Under the insulation, on a hot pipe. In the biofilm slime on a ship's hull. At the waterline where waves endlessly wash. In the thread-like filaments spreading under paint. In the hydrogen atoms creeping through high-strength steel. Invisible processes. Hidden locations. Unexpected mechanisms. The mystery of corrosion reveals new depths. We think we understand it. We think we're watching for it. And then it surprises us by attacking from a direction we didn't anticipate. When we return, we'll explore the weapons in our arsenal. The technologies and techniques humans have developed to fight back against corrosion in all its forms. Sleep well. The hidden corrosion continues its patient work, but soon we'll discover how humanity defends itself against this invisible, unexpected enemy. Welcome back. Breathe deeply and let tranquility wash over you. We've explored how corrosion attacks, where it hides, how it surprises us. But humanity is not defenseless. Nature itself has provided certain materials with remarkable resistance to corrosion. Tonight, we explore materials that fight back, the metals and alloys that resist the electrochemical enemy through their own inherent properties. Let's begin by clarifying something we touched on earlier, a distinction that matters more than it might seem. Only iron rusts. Metals like aluminum and copper form different corrosion products. This isn't merely semantic. It reflects fundamental differences in how various metals interact with their environment and how their corrosion products behave. Rust is iron oxide, that flaky, porous, reddish-brown material that forms on corroding iron and steel. Rust's defining characteristic, the thing that makes it so destructive, is that it doesn't protect the underlying metal. It constantly flakes away, exposing fresh metal to attack. Rust is permeable to moisture and oxygen, so corrosion continues unabated beneath the rust layer. This is why iron and steel corrode so readily, and why rust can completely consume unprotected iron given enough time. But other metals form very different corrosion products. These products often have entirely different properties, different colors, different structures, different protective qualities. Understanding these differences is key to understanding why some metals resist corrosion so much better than iron. Aluminum, for instance, doesn't rust. It corrodes, yes, but it forms something altogether different. Aluminum forms a thin oxide layer that slows further corrosion. This aluminum oxide film, chemically Al2O3, is remarkable. It forms almost instantly when aluminum is exposed to air. Within nanoseconds of cutting or scratching aluminum, a new oxide film has already begun forming on the freshly exposed surface. This oxide layer is extraordinarily thin, typically only a few nanometers thick, far thinner than a human hair. You cannot see it. The aluminum surface looks shiny and metallic because the oxide film is so thin that light passes through it easily. Yet despite its thinness, this layer provides tremendous protection. Aluminum oxide is dense, non-porous, and tightly adherent to the underlying metal. Unlike rust, which flakes away, aluminum oxide clings tenaciously. It forms a barrier that oxygen and moisture cannot easily penetrate. The aluminum beneath is sealed away from the environment, and corrosion essentially stops. This is why aluminum doesn't visibly corrode in most everyday environments. An aluminum can or window frame can remain outdoors for years without significant deterioration. The oxide layer protects it. Oh, the aluminum is technically corroding. That oxide layer is the result of corrosion. But once the thin protective film forms, further corrosion proceeds extremely slowly. This self-protection is called passivation, and aluminum is one of nature's best examples. The metal actively protects itself through its own corrosion product. If the oxide layer is scratched or damaged, it heals immediately as fresh aluminum underneath reacts with oxygen to form new oxide. But aluminum isn't the only metal that passivates. There's an entire class of steel that relies on this principle. Stainless steel resists rust through chromium-rich oxide films. Stainless steel is not a single alloy, but a family of alloys, all containing significant amounts of chromium, typically at least 11 or 12% by weight. This chromium is the key to stainless steel's remarkable corrosion resistance. Like aluminum, chromium forms a passive oxide film when exposed to air or moisture. This chromium oxide layer, enriched at the surface of the stainless steel, acts as a barrier preventing the underlying iron from corroding. The steel beneath contains iron, yes, and that iron would rust if exposed. But the chromium oxide film keeps it sealed away. The film is invisible, just a few atomic layers thick, but incredibly protective. It gives stainless steel its characteristic resistance to atmospheric corrosion, its ability to resist many chemicals, and its general durability in corrosive environments that would quickly destroy ordinary carbon steel. Different grades of stainless steel contain different amounts of chromium and different additional alloying elements like nickel, molybdenum, or nitrogen. These variations tune the properties. Some stainless steels resist acids. Some resist chloride pitting. Some remain strong at high temperatures. But all rely fundamentally on that protective chromium oxide film. Like aluminum oxide, the chromium oxide film is self-healing. Scratch stainless steel, and the fresh surface instantly repassivates as chromium reacts with oxygen. This self-healing property means stainless steel can withstand minor damage without losing its corrosion resistance. However, the passive film only forms and remains stable in oxidizing environments. Deprive stainless steel of oxygen, trap it in a crevice with aggressive chemistry, or expose it to reducing acids, and the passive film breaks down. Then the underlying iron corrodes just as readily as ordinary steel. This is why stainless steel, despite its name, can still suffer from crevice corrosion, pitting in chlorides, and other localized attacks. It's not actually stainless. It's stain-resistant when conditions allow passivity. But if chromium-containing steel can be so resistant, imagine what happens with metals that form even more stable, even more protective oxide films. Titanium's oxide layer reforms instantly, giving it exceptional corrosion resistance. Titanium might be the ultimate self-protecting metal. Its oxide film, titanium dioxide or TO2, is extraordinarily stable and forms with remarkable speed. Damage the oxide layer on titanium, scratch it, abrade it, chemically attack it, and within milliseconds, a new film has formed. The reaction is so fast, the healing so immediate, that maintaining a bare titanium surface in any oxygen-containing environment is essentially impossible. This gives titanium corrosion resistance, surpassing even the best stainless steels. Titanium resists seawater, chlorides, acids, and industrial chemicals that would attack stainless steel. It's used in chemical processing equipment, marine applications, biomedical implants, and anywhere maximum corrosion resistance is needed. The downside? Titanium is expensive. It's difficult to extract from ore and challenging to fabricate. A titanium component might cost 10 or 20 times more than the same component in stainless steel. So titanium is reserved for applications where its exceptional properties justify the cost. But titanium's passivity, however impressive, still involves chemical reaction and oxide formation. There are metals that take corrosion resistance to an even higher level, metals that barely react at all. Gold and platinum barely corrode due to their noble electrochemical nature. These are the noble metals, so called because they stand apart from common metals in their reluctance to react. Electrochemically, they have very positive potentials. They don't want to give up electrons. They don't want to oxidize. They resist corrosion not through protective films, but through sheer chemical reluctance to react. Gold is perhaps the most noble of all common metals. It doesn't tarnish. It doesn't rust or corrode under any normal environmental conditions. A gold artifact buried for 3,000 years emerges, looking much as it did when first made. This permanence, this refusal to change, is why gold has been treasured throughout human history. Platinum, palladium, rhodium, and other platinum group metals share this nobility. They resist even aggressive chemicals. Platinum crucibles are used in laboratories precisely because platinum won't react with the materials being heated in it. The nobility of these metals makes them invaluable for certain applications. Gold is used in electronics because connections must remain reliable for years without corroding. Platinum is used in catalytic converters, sensors, and chemical processing equipment. These metals work where everything else would fail. But nobility comes at a price. These metals are rare and expensive. You cannot build a bridge from gold or a pipeline from platinum. They're reserved for small, critical applications where cost can be justified. And this touches on a fundamental truth about materials and corrosion. Some alloys trade hardness and strength for better corrosion resistance. Materials science is full of trade-offs. You can have high strength, or you can have excellent corrosion resistance, but achieving both simultaneously is challenging. High-strength steels, hardened through alloying and heat treatment, are often more vulnerable to corrosion than mild steel. The same metallurgical features that provide strength, fine precipitates, high dislocation densities, residual stresses, can also make the material more susceptible to stress corrosion cracking, hydrogen embrittlement, and localized attack. Conversely, the most corrosion-resistant materials often aren't particularly strong. Pure aluminum is soft and weak, though its oxide layer provides excellent corrosion protection. Add alloying elements to strengthen the aluminum, and you often reduce corrosion resistance. The high-strength aluminum alloys used in aircraft require protective coatings precisely because their alloying additions make them more vulnerable to corrosion than pure aluminum. Engineers constantly navigate these trade-offs. For a structural member under high stress, strength may be paramount, and extra corrosion protection through coatings or cathodic protection can compensate for using a less corrosion-resistant material. For a non-structural component in a harsh environment, prioritizing corrosion resistance makes sense even if it means accepting lower strength. Sometimes the ideal solution is a combination: a strong structural material protected by a coating or cladding of a more corrosion-resistant material. Use the right material in the right place, matched to the application's specific demands. And nowhere is the balance between strength, weight, and corrosion resistance more critical than in aviation. Aluminum aircraft rely on self-healing oxide layers for protection. The aluminum alloys used in aircraft structures are engineering marvels. They must be strong enough to withstand flight loads, light enough to enable efficient flight, tough enough to resist crack growth, and corrosion-resistant enough to survive decades of service in varying climates. The aluminum-copper alloys, aluminum-zinc alloys, and aluminum-magnesium alloys that form aircraft structures all rely fundamentally on that same protective oxide film we discussed earlier. Damage the surface, and it instantly repassivates. This self-protection allows aluminum aircraft to operate in humid, salty, coastal environments without dissolving away. But aircraft aluminum isn't perfectly corrosion-resistant. The alloying elements that provide strength, copper, zinc, magnesium, create electrochemical heterogeneity within the alloy. Some phases are more anodic, some more cathodic. This sets up conditions for localized corrosion, particularly pitting and intergranular attack. To manage this, aircraft aluminum is often clad with a thin layer of higher purity aluminum. This cladding, typically just a few percent of the total thickness, provides enhanced corrosion protection to the higher strength core alloy beneath. The cladding corrodes preferentially if damage occurs, sacrificially protecting the structural material. Aircraft also receive elaborate protective coatings, are regularly washed to remove salt and contaminants, and are inspected frequently for corrosion. Commercial airliners might be thoroughly inspected for corrosion every few years, with suspect areas stripped down to bare metal for detailed examination. The result is that aluminum aircraft, properly maintained, can serve for 30, 40, even 50 years. Some World War II-era aircraft still fly today, 80 years after manufacture, protected by that persistent, self-healing oxide layer and careful maintenance. But aluminum, corrosion-resistant as it is, isn't the lightest metal available. There's something even lighter, though far more challenging to use. Magnesium alloys corrode easily, but are valued for low weight when protected. Magnesium is about 2/3 the density of aluminum, making it the lightest structural metal in common use. For applications where every gram matters, aerospace, automotive, portable electronics, magnesium's low weight is extremely attractive. But magnesium is electrochemically very active. It's near the anodic end of the galvanic series, eager to corrode. Magnesium's oxide film, unlike aluminum's, is not particularly protective. It's porous and doesn't seal the metal effectively. Magnesium corrodes readily in moist environments, and the corrosion can accelerate rapidly once initiated. So why use magnesium at all? Because when properly protected, it provides weight savings that justify the extra effort. Magnesium components can be coated with conversion coatings, painted, or anodized to provide barrier protection. They can be designed to avoid galvanic contact with more noble metals. They can be used in relatively dry, controlled environments where corrosion is minimal. Magnesium castings are used in automotive engine blocks, transmission cases, and structural components. Magnesium alloys appear in aircraft components, camera bodies, and laptop housings. In each case, the weight savings are valuable enough to warrant the corrosion protection measures required. Interestingly, magnesium's high electrochemical activity is also useful. Magnesium makes excellent sacrificial anodes for cathodic protection, corroding readily to protect steel structures. The same property that makes magnesium difficult to use structurally makes it valuable as a protective element. But sometimes, a metal's corrosion product, rather than being a problem to manage or a protective layer to maintain, becomes a defining aesthetic feature. The Statue of Liberty's green patina now protects the copper beneath. Stand in New York Harbor and look up at Lady Liberty. Her distinctive green color is not paint. It's patina, a layer of copper carbonate and copper sulfate that has formed over more than a century of exposure to urban and marine atmosphere. When the statue was first erected in 1886, it gleamed with the reddish-orange color of fresh copper. But copper, exposed to air and moisture, gradually oxidizes. First, it darkens to brown as copper oxide forms. Then, over years and decades, the oxide continues reacting with carbon dioxide and sulfur compounds in the atmosphere, forming basic copper carbonate, that characteristic green compound we call patina or verdigris. This transformation alarmed people when it first became noticeable. There were proposals to strip the patina and restore the statue's original copper color, or to paint it. But wiser voices prevailed. The patina, it turns out, is protective. Like aluminum oxide, it forms a barrier layer that prevents further corrosion of the copper beneath. The statue's green color has become iconic, so familiar that many people don't realize the statue was ever a different color. The patina is now considered part of the monument's character, its history visible in its very surface. This same principle applies to copper roofs on old buildings, bronze sculptures in public spaces, and weathering steel structures designed to form stable rust layers. Sometimes, allowing controlled corrosion to form a protective layer is the best long-term strategy. As you rest now, feeling sleep approaching, consider this final insight about materials and corrosion. Material choice often determines whether corrosion becomes a crisis or a footnote. Two identical structures, one built from carbon steel and one from stainless steel, will have vastly different maintenance requirements and lifespans. A pipeline made from the wrong alloy for its environment might last just years. Make it from the right material, and it could last decades. Engineers must understand the environment, understand the material options, understand the trade-offs between cost, strength, fabricability, and corrosion resistance. Sometimes, spending more initially on a corrosion-resistant material saves enormous expense over the structure's lifetime. Other times, using a less expensive material with good protective coatings and maintenance proves more economical. There's no universal answer. Context matters. Service environment, expected lifetime, maintenance access, consequences of failure, budget constraints, all factor into material selection. But the fundamental truth is clear. Some materials fight back against corrosion. They passivate, forming protective barriers. They heal themselves when damaged. They simply refuse to react. Understanding these materials, knowing their strengths and limitations, is central to winning the war against corrosion. Think of aluminum aircraft lasting decades through self-healing oxides. Titanium medical implants spending lifetimes in the human body without corroding. Stainless steel enduring where carbon steel would fail in months. Platinum sensors lasting years in exhaust gases hot enough to glow. The Statue of Liberty standing proud, her green patina both badge of age and shield against further decay. These materials don't eliminate corrosion. Aluminum still oxidizes. Stainless steel still forms its chromium-rich layer. Copper still develops its patina. But they transform corrosion from an enemy into something manageable, sometimes even beneficial. The corrosion products protect rather than destroy. The materials adapt and endure. Rest now. Let your mind settle on the image of that green statue in the harbor, standing against salt spray and industrial pollution for over a century, protected by its own corrosion product. Or picture the aluminum skin of an aircraft, scratched by ground handling, yet instantly repassivating, sealing itself against the corrosive atmosphere. Materials that fight back. Metals that protect themselves. Nature's own solutions to the problem of corrosion, discovered through chemistry and metallurgy, applied through human ingenuity. When we return, we'll explore the other weapons in our arsenal. The active measures humans take to protect materials that don't naturally resist corrosion. The coatings, the electrical systems, the chemical treatments, all the ways we impose protection on vulnerable metals. Sleep well. The self-protecting metals stand guard, their oxide shields formed and ready, requiring no intervention to maintain their resistance. But for the vast amount of steel and iron in our infrastructure, we must provide protection. Soon, we'll see how. Welcome back. Let yourself sink deeper into comfort. Release any tension remaining in your body. We've explored materials that naturally resist corrosion through their own chemistry. But most of our infrastructure is built from steel, strong, affordable, versatile, but vulnerable to rust. For these materials, we must provide protection. Tonight, we explore coatings, protection, and sacrifice. The technologies humans have developed to shield vulnerable metals from corrosion's relentless attack. Imagine a freshly manufactured steel beam. The surface is clean, perhaps slightly oiled to prevent rust during storage. This beam will become part of a bridge, exposed to rain, humidity, temperature swings, and perhaps road salt spray. Left unprotected, it would begin rusting within days. Within years, significant metal loss would occur. Within decades, the beam might need replacement. But with proper protection, this beam could last a century or more. The simplest, oldest form of protection is also still one of the most effective. Protective coatings act as physical barriers against oxygen and water. The principle is straightforward. Corrosion requires an electrolyte, typically water containing dissolved ions. It requires oxygen for the cathodic reaction. If you can keep these away from the metal surface, corrosion cannot proceed. A coating, whether paint, plastic, ceramic, or metal, interposes itself between the environment and the metal. Rain falls on the coating, not the steel. Oxygen in the air cannot reach the metal surface. The electrochemical circuit cannot complete. Corrosion stops, or at least slows dramatically. Paint is the most familiar protective coating. Humans have been painting metal for protection for centuries. The paint film, when intact, prevents moisture from reaching the metal. Modern paints contain pigments that may also provide additional protection, zinc-rich primers. For instance, add sacrificial protection, even if the coating is breached. But a single layer of paint, however carefully applied, is not perfect. Microscopic pores might exist. The coating might be too thin in spots. Mechanical damage or weathering can create defects. This is why serious corrosion protection uses more sophisticated approaches. Modern coating systems often use multiple layers for durability. Professional corrosion protection isn't just slapping on a coat of paint. It's a carefully engineered system with multiple layers, each serving specific functions. The system typically begins with surface preparation. This is absolutely critical. Paint applied over rust, mill scale, or contamination will fail quickly. Professional surface preparation might involve abrasive blasting to white metal, removing every trace of rust and scale, leaving a clean, rough surface that paint can grip. Then comes the primer layer. This coating is applied directly to the bare metal and must bond tenaciously to the surface. Primers often contain active pigments, zinc, aluminum, or phosphate compounds that provide sacrificial or passivating protection. The primer's job is to protect the metal directly and provide a good foundation for subsequent layers. Next, intermediate coats may be applied. These build thickness, improve impact resistance, and provide additional barrier properties. They fill any small defects in the primer and create a uniform surface for the top coat. Finally, the top coat is applied. This outer layer faces the environment directly. It must resist UV radiation from sunlight, resist weathering and mechanical abrasion, shed water, and maintain its appearance. Top coats often contain UV stabilizers, wear-resistant pigments, and flexible resins that can expand and contract with temperature changes without cracking. The total system might be 300 to 500 micrometers thick, less than half a millimeter. But those multiple layers, properly applied, can protect steel for 20, 30, even 50 years before requiring maintenance. Each layer has its role. Remove any layer, and protection is compromised. The primer protects the metal directly. The intermediate coats provide barrier properties and thickness. The top coat resists environmental attack. Together, they form a system far more effective than any single layer could be. But paint, however sophisticated, is an organic coating. There are other approaches using metal itself as the protective layer. Hot-dip galvanizing coats steel with zinc for decades of protection. Walk past galvanized steel and you'll recognize it. That distinctive spangled, silvery gray appearance. Galvanized steel is everywhere. Highway guardrails, utility poles, building frameworks, chain-link fences, fasteners, and countless other applications. The galvanizing process is elegantly simple. clean steel is dipped into a bath of molten zinc at about 450 degrees Celsius. The zinc reacts with the iron at the surface, forming zinc-iron alloy layers. When the steel is withdrawn, a layer of pure zinc coats the surface, typically 75 to 150 micrometers thick. This zinc coating protects the steel in two ways. First, it's a barrier layer. As long as the zinc remains intact, the steel beneath is sealed away from moisture and oxygen. Second, and more importantly, zinc is sacrificial. Zinc is more electrochemically active than iron. If the coating is scratched or damaged, exposing steel, the zinc around the damage corrodes preferentially, protecting the exposed steel cathodically. In atmospheric exposure, zinc corrodes much more slowly than unprotected steel, roughly 10 to 20 times slower, depending on environment. In rural atmospheres, galvanized steel might corrode at just a few micrometers per year. Even in industrial or marine environments, galvanizing provides decades of protection. The thickness matters. A coating of 100 micrometers, corroding at 5 micrometers per year, will last 20 years before the steel is exposed. In practice, galvanized steel often lasts even longer because zinc's own corrosion products, zinc oxide and zinc carbonate, are somewhat protective, slowing further zinc loss. Hot-dip galvanizing is economical and durable. It's why so much outdoor steel infrastructure is galvanized. The initial cost is modest compared to the decades of maintenance-free service provided. And the principle of using a more active metal to protect steel extends beyond coatings to deliberate, renewable sacrificial elements. Sacrificial anodes corrode preferentially to protect steel structures. This is cathodic protection through galvanic action, the same phenomenon that causes galvanic corrosion when it occurs accidentally, but now harnessed intentionally for protection. Picture an underground steel pipeline. Even with a protective coating, tiny holidays, small defects, might expose bare steel to soil. Normally, these would corrode, the defects would grow, and eventually the pipeline would leak. But attach zinc or magnesium anodes to the pipeline at intervals, electrically connected through the pipeline itself, and everything changes. The zinc or magnesium is more electrochemically active than steel. It becomes the anode of a galvanic cell, corroding and releasing electrons. These electrons flow through the pipeline to the bare steel areas, which become cathodic. At cathodic sites, corrosion cannot occur. Instead, oxygen reduction or hydrogen evolution proceeds. The steel is protected. The anode is consumed. This is why it's called sacrificial protection. The zinc or magnesium anode sacrifices itself, corroding away, so that the steel structure is preserved. It's a controlled corrosion, directing the electrochemical attack to expendable elements that can be easily replaced. Ship hulls use zinc anodes. Water heaters have magnesium anodes built in. Offshore platforms have arrays of aluminum anodes attached to their legs. Underground tanks and pipes have magnesium ribbon anodes buried nearby. The anodes gradually dissolve away and must be replaced periodically, but the protected structure endures. The economics are compelling. An anode might cost a few $100s and last 5 to 10 years. Replacing corroded pipeline sections or a perforated storage tank costs many thousands, or even millions of dollars. The sacrificial anode system prevents this damage for a tiny fraction of the cost. But sacrificial anodes have limitations. Their driving voltage is fixed by electrochemistry. In high-resistivity soils or large structures, the current they can provide may be insufficient. For these cases, there's a more powerful approach. Impressed current cathodic protection uses external power to suppress corrosion. Instead of relying on galvanic action, impressed current systems use an external power source, typically a rectifier converting AC power to DC, to force current onto the structure. Inert or dimensionally stable anodes are placed in the environment, perhaps buried in the soil near a pipeline or suspended in seawater near a ship's hull. The negative terminal of the power source connects to the structure being protected. The positive terminal connects to the anodes. Current flows from the anodes through the environment onto the structure and back through the electrical connection to complete the circuit. This forces the entire structure to become cathodic. Corrosion reactions cannot proceed at cathodic sites. The externally supplied electrons suppress metal dissolution. The beauty of impressed current is its controllability. The voltage and current can be adjusted to provide exactly the protection needed. A control system might monitor the structure's potential and automatically adjust the power to maintain optimal protection levels. Too little current, and protection is incomplete. Too much, and problems like hydrogen embrittlement or coating disbondment can occur. Just right, and the structure is perfectly protected. Impressed current systems protect vast networks. Thousands of miles of pipeline might be protected by systems spaced every few miles along the route. Entire offshore platforms are protected by impressed current. Large ships, port facilities, storage tank farms, all can use impressed current cathodic protection. The ongoing cost is electricity. The system must run continuously. But this cost is modest compared to corrosion damage prevented. A pipeline cathodic protection system might consume just a few hundred watts per station, perhaps $100 per year in electricity. The protection provided is worth millions. But protection doesn't always require exotic technologies or sacrificial metals. Sometimes, simple chemical treatments provide effective protection. Phosphating improves paint adhesion and provides sacrificial protection. If you've ever seen automotive components or appliances before painting, you might have noticed a dull grey crystalline coating. This is phosphate conversion coating, a standard pre-treatment for steel before painting. The phosphating process involves exposing clean steel to an acidic solution containing phosphate ions and metal ions, typically zinc, iron, or manganese. The acid etches the steel surface slightly. Phosphate reacts with dissolved metal ions to form insoluble metal phosphate crystals that deposit on the steel surface, creating a thin layer of crystalline phosphate, usually 5 to 25 micrometers thick. This phosphate layer provides multiple benefits. Its rough, crystalline structure gives paint excellent mechanical grip. The phosphate converts the reactive steel surface into a more stable, less active surface. And the phosphate layer itself provides some sacrificial protection. If moisture reaches the steel through coating defects, the phosphate dissolves, releasing phosphate ions that inhibit corrosion. Phosphating is inexpensive and fast. Parts pass through the phosphate bath in just minutes. Nearly all painted steel products receive phosphate treatment. Automobiles, appliances, furniture, electrical enclosures. It's a simple process with enormous impact on coating performance and product durability. And just as steel can receive chemical conversion coatings, aluminum can be treated to enhance its natural protective oxide. Anodizing thickens aluminum's oxide layer for enhanced resistance. Remember that aluminum naturally forms a thin oxide film, just nanometers thick. Anodizing is an electrochemical process that grows this oxide layer much thicker, typically 5 to 25 micrometers, over 1,000 times thicker than the natural film. The aluminum part is made the anode in an electrolytic bath, usually containing sulfuric acid. When current flows, oxygen generated at the anode surface reacts with the aluminum, forming aluminum oxide. Unlike plating, where material deposits onto the surface, anodizing actually converts the surface aluminum into oxide. The oxide grows both outward and inward. About half the oxide thickness comes from the original metal surface. The other half builds upward. The result is an oxide layer integral to the metal, impossible to peel off because it's not a coating, but a transformation of the surface itself. This thick oxide dramatically improves corrosion resistance compared to bare aluminum. It also provides a hard surface resistant to wear and scratching. Anodized aluminum can also be dyed. The oxide structure is porous before sealing, and dyes can penetrate these pores, giving anodized aluminum bright, durable colors. After dyeing, the pores are sealed with boiling water or other treatments, trapping the dye and further improving corrosion resistance. Architectural aluminum, aircraft components, consumer electronics, countless applications use anodizing. It's one of the most successful and widely used surface treatments for aluminum. But not all protective coatings are applied as liquids. There's a technology that applies coatings as powder, creating particularly durable finishes. Powder coatings provide tough, uniform protective films. Instead of paint suspended in solvents, powder coating uses finely ground particles of pigment and resin. These particles are electrostatically charged and sprayed onto grounded metal parts. The charged powder adheres to the metal through electrostatic attraction. The coated part then enters an oven. The powder melts, flows together, and cures into a continuous film. The result is a coating typically 50 to 100 micrometers, thick with excellent uniformity and few defects. Powder coating offers several advantages. There are no solvents, making it environmentally friendly. The application efficiency is high. Overspray powder can be collected and reused. The coatings are thick, tough, and resistant to chipping and scratching. And the process is suitable for mass production, with automated systems coating hundreds of parts per hour. You see powder-coated products everywhere. Outdoor furniture, bicycles, appliances, automotive parts, architectural elements. Powder coating provides durable, attractive protection to countless steel and aluminum products. The technology continues advancing. New powder formulations improve weatherability, provide antimicrobial properties, or create special surface textures. Powder coating is becoming the standard for many applications that once used liquid paints. And for the most demanding applications, where both corrosion protection and high-temperature resistance are needed, advanced coating technologies embed protective alloys directly onto steel surfaces. Thermal spray and HVOF coatings embed corrosion-resistant alloys onto steel. These are sophisticated technologies used primarily in industrial applications where ordinary coatings wouldn't survive. In thermal spraying, a corrosion-resistant material, perhaps aluminum, zinc, or a nickel-based alloy, is melted and propelled at high velocity onto the steel surface. The molten droplets impact, flatten, and rapidly solidify, building up a dense coating of the protective material. HVOF stands for high-velocity oxygen fuel. In this process, fuel and oxygen combust in a specially designed gun, creating an extremely hot, supersonic gas jet. Powder particles are injected into this jet and accelerated to speeds over twice the speed of sound. The particles impact the surface with tremendous kinetic energy, creating extremely dense, well-bonded coatings. These processes can apply coatings that are essentially bulk alloy deposited onto steel. Want a steel component with a surface as corrosion-resistant as stainless steel? Spray on a stainless steel coating. Need protection from high-temperature oxidation? Apply a nickel-chrome alloy coating. The coating properties approach those of the bulk material because that's essentially what it is, just applied as a coating rather than fabricated as solid metal. Thermal spray coatings protect offshore platform legs, boiler tubes in power plants, chemical processing equipment, and aerospace components. They're more expensive than paint, but provide protection in environments where paint would fail immediately. High temperatures, abrasive conditions, extreme chemical exposure. And some coatings go beyond merely blocking the environment, actually releasing chemicals that inhibit corrosion. Some coatings also release inhibitors that slow corrosion chemically. These are sometimes called smart coatings because they respond to damage by releasing protective chemicals. The coatings contain capsules or reservoirs of corrosion inhibitors embedded in the coating matrix. When damage creates a defect in the coating, moisture penetrating the defect contacts these inhibitor reservoirs. The inhibitors release into the moisture film at the metal surface, altering the local chemistry to suppress corrosion. Inhibitors work through various mechanisms. Some make the metal surface passive, strengthening protective oxide films. Some precipitate at anodic sites, blocking metal dissolution. Some poison cathodic reactions. The specific inhibitor is chosen based on the metal being protected and the expected corrosion mechanisms. Chromate inhibitors were once widely used and were extremely effective, but environmental and health concerns have largely eliminated them. Modern research focuses on finding equally effective, but safer alternatives. rare earth inhibitors, phosphate compounds, organic inhibitors. Self-healing coatings take this concept further, with capsules that not only release inhibitors, but also release coating-forming materials that seal damage. Scratch such a coating, and it literally heals itself, resealing the defect before corrosion can initiate. These technologies are still relatively new and expensive, but they represent the future of corrosion protection. Intelligent systems that adapt and respond, providing protection that goes beyond simple barriers. As you rest now, drifting deeper towards sleep, consider the layers of protection we've built around vulnerable metals. The multiple layers of paint, each with its specific function. The silvery zinc coating protecting countless steel structures. The magnesium anodes gradually dissolving to save pipelines. The invisible current flowing from impressed current systems. The crystalline phosphate layer gripping paint to steel. The thick anodized oxide on aluminum. The tough powder coating resisting chips and scratches. The high-velocity spray coatings embedding protective alloys. The smart coatings releasing inhibitors when damaged. Layer upon layer. Technology upon technology. Each adding protection. Each extending the life of steel and other metals. Each pushing back against corrosion's persistent attack. It's a testament to human ingenuity. We cannot eliminate corrosion. Thermodynamics is against us. Refined metals want to return to their oxidized state. But we can slow corrosion dramatically. We can manage it, control it, direct it to expendable elements, block it with barriers, suppress it with electrical current, inhibit it with chemistry. A properly protected steel structure can last a century or more. That's not forever, but it's long enough. Long enough for bridges to carry millions of vehicles. Long enough for buildings to shelter generations. Long enough for pipelines to deliver fuel and water and materials that build prosperity. The coatings weather and age. The sacrificial anodes dissolve. The cathodic protection systems consume electricity. Maintenance is required. Inspection is necessary. But with these technologies, properly applied and maintained, we extend the useful life of infrastructure far beyond what unprotected metal could achieve. Rest now. Picture a newly painted bridge gleaming in sunlight, its multi-layer coating system protecting the steel beneath. Or a galvanized highway railing, zinc-coated and ready to serve for decades. Or a pipeline deep underground, its coating intact, its cathodic protection current flowing, safe from the corrosive soil around it. Protection and sacrifice. Barriers and currents. Coatings and chemistry. This is how humanity fights back. How we protect the metal foundations of modern civilization from the slow, patient enemy that is corrosion. When we return, we'll explore how we detect corrosion, how we monitor its progress, and how we know when protection is working or failing. The invisible enemy requires vigilant watching, and we've developed sophisticated eyes to see what would otherwise remain hidden. Sleep well. The protective systems stand guard, layer upon layer, technology upon technology, holding back the electrochemical forces that would consume our infrastructure. For now, they hold. For now, we are protected. Welcome back. Let yourself settle even deeper now. Feel the weight of your body supported completely. We've explored how corrosion attacks and how we protect against it. But protection is not permanent. Coatings age. Anodes deplete. Conditions change. Tonight, we explore watching the enemy. The constant vigilance required to manage corrosion before it becomes catastrophic. Take a slow, deep breath and consider a sobering truth that every corrosion engineer knows. Corrosion cannot be stopped completely, only managed. This is perhaps the most important lesson in all of corrosion engineering. There is no perfect solution, no permanent fix, no coating that lasts forever, no cathodic protection system that requires zero maintenance, no material that never degrades. Thermodynamics is relentless. Refined metals exist in a high-energy state. Nature wants them to return to their lower-energy oxidized forms. We can slow this process dramatically. We can redirect it. We can control where and how it occurs. But we cannot stop it permanently. Even the most sophisticated protection systems eventually fail. Coatings crack and degrade with UV exposure and weathering. Cathodic protection anodes deplete and must be replaced. Inhibitors wash away and lose effectiveness. Materials that passivate can still suffer localized attack under the wrong conditions. This means corrosion is not a problem you solve once and forget. It's an ongoing challenge requiring continuous attention. Infrastructure must be monitored. Protection systems must be maintained. Damage must be detected before it becomes critical. This is the reality of living with metals in corrosive environments. Accepting this reality is liberating in a way. You stop looking for perfect solutions that don't exist. Instead, you focus on management, on detection, monitoring, maintenance, and timely intervention. And the foundation of good corrosion management is knowing what's happening to your equipment. Regular inspection is critical to preventing catastrophic failures. Inspection is not glamorous. It's time-consuming. It's expensive. It often finds nothing wrong, which can feel like wasted effort. But inspection is absolutely essential because corrosion damage, left undetected, progresses until failure occurs. History is littered with catastrophic failures that could have been prevented by timely inspection. Bridges that collapsed, pipelines that ruptured, storage tanks that leaked, aircraft that crashed. In many cases, post-failure investigation reveals that warning signs existed, corrosion damage that had progressed for years unnoticed. The failure wasn't sudden at all. It was the final event in a long process of deterioration that could have been caught by inspection. Regular inspection serves multiple purposes. It detects active corrosion before it becomes critical. It verifies that protective systems are working as intended. It identifies areas where conditions have changed, perhaps where coatings have been damaged, or where new sources of moisture or contamination have appeared. It provides data for trending, watching how conditions evolve over time so problems can be anticipated before they develop. The challenge is that infrastructure is vast. Consider a refinery with thousands of vessels, heat exchangers, and miles of piping, or a pipeline network spanning continents, or a fleet of aircraft, each with thousands of components. Inspecting everything thoroughly is impossible. Resources are finite, so inspection programs must be risk-based. Critical equipment gets inspected more frequently. Areas prone to corrosion receive extra attention. High-consequence systems, those where failure would be catastrophic, are monitored closely. Less critical areas are checked less often. The art is in optimizing the inspection effort to find problems before failures occur, while not consuming unlimited resources inspecting everything constantly. But how do you inspect for corrosion, especially when it's hidden inside pipes or beneath insulation or within structures? This is where technology becomes crucial. Ultrasonic testing measures wall thickness without cutting equipment open. Ultrasonic testing, or UT, is one of the most widely used non-destructive testing methods for corrosion monitoring. It works on a simple principle. Sound waves travel through solid material and reflect from the opposite surface. A technician places an ultrasonic transducer against the outside of a pipe or vessel wall. The transducer emits a pulse of high-frequency sound, far above human hearing, typically 1 to 10 MHz. This sound pulse travels through the metal. When it reaches the inner surface, it reflects back. The transducer detects this echo. By measuring the time between sending the pulse and receiving the echo, and knowing the speed of sound in the material, the thickness can be calculated precisely. Typical accuracy is within a few hundredths of a millimeter. The entire measurement takes just seconds. The beauty of UT is that you can measure thickness from one side only. You don't need to cut the pipe open. You don't need to access the inside. Just place the transducer on the outer surface, and you can determine how much metal remains. For corrosion monitoring, the same locations are measured periodically. Perhaps a pipe is measured this year and found to be 8.5 millimeters thick. Measured again in 2 years, it's 8.2 millimeters. The corrosion rate is clearly 0.15 millimeters per year. Project forward, and you can estimate when the wall will thin to the minimum allowable thickness, allowing maintenance to be planned before failure occurs. Modern UT systems can scan large areas quickly. Automated systems crawl along pipelines or inside vessels, collecting thickness data at thousands of points. The data builds a map showing where corrosion is occurring and how severe it is. Areas of concern stand out clearly, guiding more detailed inspection or repair. But ultrasonic testing only measures thickness. It doesn't show you what the corrosion looks like or reveal damage that doesn't thin the wall uniformly. For that, other methods are needed. Radiography reveals internal corrosion hidden from view. Radiographic testing uses X-rays or gamma rays, just like medical radiography, but aimed at metal structures instead of human bodies. The radiation penetrates the metal, and a detector on the opposite side records how much radiation passes through. Thicker metal absorbs more radiation. Thinner areas, corroded areas, voids, or cracks allow more radiation through. The resulting image, the radiograph, shows the internal structure and condition of the component. It's like an X-ray revealing the skeleton beneath the skin. Radiography can detect internal corrosion in complex geometries where ultrasonic testing might not work. It can find corrosion under deposits or scale that would interfere with ultrasound. It can reveal the shape and extent of pitting or other localized attack. And it creates a permanent record, a film or digital image that can be reviewed later or compared to future radiographs to track progression. The downsides are that radiography requires access to both sides of the component. It's slower than ultrasonic testing, and it involves ionizing radiation requiring safety controls. But for critical welds, for complex castings, for situations where you need to see inside the metal, radiography is invaluable. Advanced techniques like computed tomography, CT scanning for metal, can create three-dimensional images showing internal damage in exquisite detail. These methods are expensive and time-consuming, but provide unmatched insight into hidden corrosion. Yet both UT and radiography are periodic measurements. A technician comes, performs the test, records the data, and leaves. What about continuous monitoring? What if you want to know what's happening right now, all the time? Corrosion coupons measure real-world corrosion rates over time. This is one of the oldest and simplest corrosion monitoring methods, yet it remains widely used because it works. A corrosion coupon is simply a small piece of metal, often the same material as the equipment being monitored, that's exposed to the same corrosive environment. The coupon is carefully cleaned, weighed precisely, and installed in the system. It might be inserted into a pipe, hung inside a vessel, or buried alongside a pipeline. It's left in place for a set period, perhaps 3 months, 6 months, or a year. Then it's removed, cleaned of corrosion products, and weighed again. The weight loss directly indicates how much metal corroded away. Since you know the surface area and the exposure time, you can calculate the corrosion rate in millimeters per year or mils per year. This is real-world corrosion under actual operating conditions, not a laboratory simulation or a theoretical prediction. Coupons are inexpensive. They require no electronics or power. They're completely reliable, just metal exposed to the environment, following the laws of electrochemistry. And they provide integrated average corrosion rates over the exposure period. The disadvantage is that they're not real-time. You must wait for the exposure period to end, remove the coupon, and analyze it. By the time you have results, conditions may have changed. If corrosion suddenly accelerates, you won't know until the next coupon is retrieved, which might be months away. For continuous, real-time information, more sophisticated instruments are needed. Online probes track corrosion rates in real time. Modern corrosion monitoring increasingly relies on probes that provide continuous data, allowing operators to see corrosion rates change as they happen rather than waiting weeks or months for coupon results. Electrical resistance probes are common. These contain a thin metal element exposed to the corrosive environment. As the element corrodes and becomes thinner, its electrical resistance increases. By continuously measuring resistance and comparing it to a reference element protected from corrosion, the system calculates metal loss in real time. Sensitivity can be excellent, detecting metal loss of micrometers over days or weeks. Linear polarization resistance probes use electrochemical measurements. A small electrode is exposed to the process fluid, and tiny currents are applied while measuring the voltage response. From this electrochemical behavior, the instantaneous corrosion rate can be calculated. These probes provide corrosion rate data updated every few minutes. Other technologies measure different parameters. Some probes detect hydrogen evolution, since many corrosion processes generate hydrogen. Some measure solution chemistry changes that indicate corrosion. Some use ultrasonic methods to continuously monitor wall thickness at a single location. The power of online monitoring is immediate feedback. If corrosion rate suddenly increases, perhaps because process conditions changed, or contamination entered the system, or a chemical treatment failed, the monitoring system detects it immediately. Operators can investigate and respond before significant damage accumulates. And this real-time information enables active corrosion management. Monitoring allows operators to adjust protection before damage accelerates. Imagine a pipeline with cathodic protection. Corrosion monitoring probes along the line continuously measure corrosion rates at various locations. The data feeds to a control center where operators watch trends. One day, corrosion rate at a particular location begins increasing. The increase is small, not yet dangerous, but noticeable. The operator investigates. Perhaps soil moisture has increased due to heavy rains. Perhaps the cathodic protection current isn't reaching the area effectively. Perhaps the protective coating has been damaged by ground movement. With this early warning, adjustments can be made. Increase the cathodic protection current. Modify drainage to reduce moisture. Plan to excavate and repair the coating. The key is that action is taken while corrosion rates are still manageable, before significant metal loss occurs. Compare this to reactive maintenance, where nothing is done until equipment fails. The pipeline corrodes for years unnoticed. One day it leaks. Now you have an emergency, contamination to clean up, interrupted service, expensive repairs under time pressure, possibly safety incidents or environmental damage. The cost in money, disruption, and risk is enormous. Proactive maintenance, guided by monitoring, is vastly preferable. Problems are caught early. Repairs are scheduled during convenient shutdowns. Failures are prevented rather than responded to. The economic case for monitoring is compelling. The cost of monitoring systems is recovered many times over through prevented failures and optimized maintenance. But monitoring is only valuable if someone pays attention to the data and acts on it. Planning for corrosion early reduces unplanned shutdowns later. This extends beyond just monitoring to encompass the entire philosophy of corrosion management. Corrosion should be considered from the very beginning, during design, material selection, and construction, not treated as an afterthought or something to deal with later. When designing a new facility, thinking about corrosion means selecting appropriate materials for each service. It means specifying proper coatings and cathodic protection. It means designing to avoid crevices and areas where water can collect. It means providing access for future inspection. It means installing monitoring systems from the start. Yes, this requires upfront investment. Corrosion-resistant materials cost more. Protective coatings add to construction costs. Monitoring systems require budget. But these costs are modest compared to the lifetime costs of corrosion damage and unplanned maintenance. An unplanned shutdown is extraordinarily expensive. A refinery processing unit shut down unexpectedly might lose $1 million per day in lost production. Emergency repairs are expensive. Overtime labor, expedited material delivery, working under time pressure. And there's reputational damage, contracts missed, customers dissatisfied, regulatory scrutiny. Compare this to a planned shutdown. Equipment is inspected on schedule. Corrosion damage is found and repaired before failure. The shutdown is scheduled when it's convenient, when materials and contractors are available, when market conditions make downtime less costly. Repairs are made methodically, correctly, without pressure. The difference in cost and disruption is enormous. Planning for corrosion, monitoring consistently, and maintaining proactively transforms corrosion from a crisis generator into a manageable aspect of operations. But even the best monitoring systems and most careful planning are useless if maintenance isn't actually performed. Maintenance failures often matter more than material failures. This is a sobering observation from failure analysis. When investigators examine why a particular corrosion failure occurred, they often find that the material performed as expected. The environment was no worse than anticipated. The protection systems were adequate, but maintenance wasn't done. The cathodic protection system was designed correctly, but the depleted anodes weren't replaced. The coating system was specified properly, but damaged areas weren't repaired. The inspection program was adequate, but the findings were ignored or deferred. The monitoring system was working, but no one looked at the data. Human factors, organizational issues, budget pressures, complacency, lack of training, poor communication, cause more failures than material or design deficiencies. The technology exists to manage corrosion effectively. The knowledge exists. The standards and best practices are documented. But knowledge must be applied, and systems must be maintained. This is why corrosion management programs emphasize documentation, training, and organizational commitment. Inspection findings must be recorded and tracked. Maintenance must be scheduled and completed. Responsibilities must be clear. Management must support the program with adequate resources and prioritization. The most corrosion-resistant material in the world will eventually fail if not maintained. Conversely, even ordinary carbon steel can provide decades of reliable service if properly coated, protected, monitored, and maintained. The difference is often not in the technology, but in the discipline of actually doing the work. And this brings us to perhaps the most important insight about corrosion management. Corrosion management is as much about vigilance as technology. All the sophisticated monitoring instruments, protective coatings, cathodic protection systems, and corrosion-resistant alloys in the world will not prevent failures if no one pays attention. Vigilance, constant, careful attention to the ongoing battle against corrosion, is what actually protects infrastructure. Vigilance means inspectors who take their work seriously, who look carefully, who report what they find honestly. It means operators who notice when monitoring data looks unusual and investigate. It means maintenance workers who repair protective coatings properly, not just slapping paint over rust. It means engineers who review corrosion trends and plan ahead. It means managers who fund inspection and maintenance even when budgets are tight. Vigilance is a cultural quality, not a technical one. Organizations with good safety cultures and good maintenance cultures tend to have good corrosion management. Organizations that cut corners, defer maintenance, and operate reactively tend to have corrosion problems regardless of their technical capabilities. The technology is important. Ultrasonic testing, radiography, corrosion probes, sophisticated coatings. These tools are valuable and necessary, but they're only tools. Human judgment, human attention, human commitment to doing the work properly. These are what actually keep corrosion under control. As you drift now, feel yourself sinking toward deeper sleep. Picture an inspector walking a pipeline route, checking cathodic protection test stations, recording readings. See a technician with an ultrasonic probe, methodically measuring pipe thickness, noting the data. Imagine an engineer reviewing monitoring trends, noticing a subtle change, deciding to investigate further. Envision maintenance workers carefully cleaning and coating a corroded area, taking pride in doing the work properly. These are the people who hold back corrosion, not through heroic efforts or dramatic interventions, but through patient, consistent, careful attention to detail. Day after day, year after year, they watch. They measure. They maintain. They prevent the catastrophic failures that make headlines by catching problems while they're still small. The technology gives them eyes to see what's happening beneath coatings, inside pipes, underground. The instruments provide data. The standards and procedures guide their work. But ultimately, it's the vigilance, the unwavering attention to the slow, patient enemy, that keeps infrastructure safe and operational. Corrosion cannot be stopped, but it can be watched, it can be measured, it can be managed, and with proper vigilance, structures can last for generations, serving reliably, safely carrying their loads, moving fluids, supporting buildings, connecting communities. Rest now. The watchers are vigilant. The instruments are measuring. The monitors are recording data. The maintenance schedules are being followed. The infrastructure stands, protected by layers of technology and human attention, defended against the electrochemical forces that would consume it. When we return, we'll explore the future, new technologies, new materials, new approaches to the ancient problem of corrosion. But for now, sleep. Sleep knowing that while you rest, others watch. Others maintain. Others hold the line against the invisible enemy. Sleep well. The vigil continues, as it must, as it always has, as it always will as long as we build with metals in corrosive environments. The price of using metals is eternal vigilance against corrosion. And humanity pays that price, day after day, keeping the infrastructure of civilization intact and functional. Welcome back for our final journey together. Let your body become completely still. Release every last bit of tension. We've traveled through the science, the costs, the mechanisms, the protections, and the vigilance required to manage corrosion. Now, as we conclude, we explore the ongoing battle. How corrosion continues to challenge us, how we continue to fight back, and what the future may hold. Tonight, we complete the mystery of corrosion. Take a deep breath and consider where corrosion matters most. Where the stakes are highest, where failure could mean not just economic loss, but threats to national security. Corrosion is a critical concern for military and defense systems. Military equipment operates in some of the most corrosive environments imaginable. Naval vessels spend months at sea, constantly exposed to salt spray and seawater. Aircraft fly through humid, salty coastal air and land on carriers in the middle of the ocean. Ground vehicles operate in deserts with blowing sand, in jungles with extreme humidity, in northern climates with road salt and freeze-thaw cycles. This equipment must remain operational despite these conditions. A fighter jet cannot be grounded because of corrosion. A tank cannot fail in combat because rust has weakened critical components. A ship's weapons systems must function after months of continuous salt spray exposure. Military readiness depends on equipment reliability, and corrosion is one of the primary threats to that reliability. But it's not just about equipment function. Corrosion directly affects safety. A corroded aircraft component could fail catastrophically mid-flight. A weakened ship structure could fail in rough seas. Corroded ammunition or weapons systems could malfunction with deadly consequences. And there's a strategic dimension. Equipment taken out of service for corrosion repairs reduces force capability. If 30% of a fleet is undergoing corrosion maintenance at any time, effective force strength is reduced by 30%. Corrosion thus directly impacts military capability and national security. This makes corrosion more than just a technical problem for the military. It's a readiness issue, a safety issue, a strategic issue, which is why the investment in fighting corrosion is so substantial. The United States Department of Defense spends billions annually fighting rust. The estimates vary, but credible studies have put the Department of Defense's annual corrosion costs at around $20 billion or more. $20 billion every year, just to manage corrosion across military systems. This includes direct costs like repairs, replacement of corroded parts, and application of protective coatings. It includes the cost of corrosion control systems, cathodic protection on ships and facilities, specialized treatments for aircraft, protective measures for vehicles and equipment. It includes inspection and monitoring to detect corrosion before it becomes critical. But it also includes indirect costs. Aircraft downtime for corrosion maintenance means training missions are delayed. Ships in dry dock for corrosion repairs cannot deploy. Corroded equipment must be replaced earlier than expected, straining procurement budgets. Personnel must be trained in corrosion inspection and prevention, time that could otherwise be spent on operational training. $20 billion represents a significant fraction of the defense budget. It's money that could otherwise buy new equipment, fund operations, or support personnel. But it must be spent because corrosion is relentless and failure is not acceptable. And within the Department of Defense, one service faces particularly severe corrosion challenges. The Navy alone spends billions each year protecting its fleet. Ships live in the ocean. They're constantly immersed in seawater, one of the most corrosive environments that exists. Salt spray coats every surface. Humidity is constantly high. Splash zones experience the most aggressive corrosion conditions imaginable. And ships cannot come ashore for maintenance frequently. They must remain operational for months at a time, operating in this harsh environment continuously. A modern naval vessel represents an investment of billions of dollars. An aircraft carrier might cost $13 billion. A destroyer costs $2 billion. A submarine costs $3 billion. These vessels are expected to serve for 30, 40, even 50 years. Protecting them from corrosion for that entire service life is an enormous challenge. The Navy uses every corrosion control technology available. Ships are coated with sophisticated paint systems applied in multiple layers. Sacrificial anodes protect the hulls. Impressed current cathodic protection systems run continuously. Dehumidification systems protect interior spaces. Corrosion-resistant alloys are used in critical components. Rigorous maintenance schedules ensure coatings are repaired and protection systems maintained. Yet despite all this, corrosion still extracts its toll. Ships require periodic dry docking for major corrosion maintenance. Structures corrode and must be repaired or replaced. Components fail due to corrosion-related damage. The Navy's annual corrosion bill runs into billions of dollars, and this is despite having some of the most sophisticated corrosion management programs in the world. The ocean is simply that aggressive. Salt water is that corrosive. The challenge of keeping steel ships operational in seawater for decades is immense, and the investment required to meet that challenge is correspondingly vast. But the military isn't alone in facing corrosion challenges in harsh coastal environments. The space program deals with similar issues. NASA treats corrosion as a major reliability risk at coastal launch sites. Consider Kennedy Space Center in Florida, located directly on the Atlantic coast, or Vandenberg Space Force Base in California, on the Pacific. These facilities are deliberately located at the coast for operational reasons. Launching over water provides safety margins and certain orbital advantages. But locating at the coast means exposure to salt spray, high humidity, and marine atmospheres, intensely corrosive conditions. And space launch vehicles cannot tolerate corrosion. A corroded fuel tank could rupture. A weakened structure could fail during launch. Corroded electrical connections could cause system failures. The consequences could be catastrophic. Loss of multi-billion-dollar spacecraft, loss of irreplaceable payloads, potential loss of life for crewed missions. So NASA implements rigorous corrosion control programs. Launch vehicles and ground systems are protected with coatings and cathodic protection. Facilities are inspected constantly. Components are monitored and replaced before corrosion becomes critical. Special corrosion-resistant materials are specified for critical applications. The Space Shuttle program experienced numerous corrosion-related issues over its 30 years of operation despite these precautions. The reusable orbiters returned from space only to be corroded by the coastal Florida environment while waiting for their next mission. Constant vigilance and maintenance were required to keep the vehicles safe and operational. Current programs like the Space Launch System and commercial launch vehicles continue to grapple with corrosion at coastal launch sites. It's an ongoing battle, requiring continuous investment and attention, because the cost of a corrosion-related launch failure would be measured not just in dollars, but in setbacks to exploration and potential loss of life. And NASA's experience reflects a broader truth about coastal environments. Coastal and marine environments corrode steel several times faster than urban air. We've mentioned this before, but it bears repeating because the difference is so dramatic. Steel exposed to rural inland air might corrode at perhaps 10 to 20 micrometers per year. In industrial urban environments, the rate might be 30 to 50 micrometers per year. But move to a coastal environment, and rates can easily reach 150 to 300 micrometers per year or more, 3 to 5 times faster, perhaps 10 times faster in the most aggressive marine splash zones. The difference is the salt. Sodium chloride from seawater becomes airborne in spray and aerosols, carried inland by wind, depositing on every surface. This salt is hygroscopic. It attracts and holds moisture even when the air seems relatively dry. And salt dramatically accelerates corrosion through multiple mechanisms. The result is that infrastructure at the coast faces extraordinary challenges. Bridges over bays and coastal highways corrode rapidly. Buildings and towers near the ocean require constant maintenance. Port facilities, offshore platforms, and coastal installations face relentless attack. This coastal corrosion penalty affects everything from military bases to civilian infrastructure, from residential buildings to industrial facilities. It's why coastal property requires more maintenance. It's why building codes in coastal zones often specify special corrosion-resistant materials and protective measures. It's why insurance and maintenance costs are higher near the ocean. The ocean gives us access to global trade, fisheries, recreation, and strategic positioning. But it exacts a price in accelerated corrosion of everything we build near it. Given these challenges across military, aerospace, and coastal infrastructure, it's fortunate that we're not fighting corrosion alone or inventing solutions from scratch every time. Codes and standards guide corrosion control worldwide. Organizations like NACE International, now part of AMPP, the Association for Materials Protection and Performance, develop standards for corrosion control practices. ASTM International publishes standards for testing methods and material specifications. The American Petroleum Institute issues guidelines for oil and gas facilities. ISO, the International Organization for Standardization, develops internationally recognized standards. These standards represent the accumulated knowledge and best practices of the corrosion community. They specify how to design cathodic protection systems, how to apply coatings properly, how to select materials for specific services, how to inspect for corrosion, how to test corrosion rates. They provide acceptance criteria, minimum requirements, and recommended practices. Following these standards doesn't guarantee perfection. Corrosion is too variable and environments too diverse for any standard to cover every situation. But standards provide a solid foundation, a starting point based on what has worked in the past. They help ensure a baseline level of competence and reduce the likelihood of basic errors. Standards also facilitate communication. When an engineer specifies that coating shall be applied in accordance with a particular NACE standard, everyone involved knows exactly what's required. When a material is specified as meeting a certain ASTM specification, suppliers and purchasers have a common understanding. The existence of these standards worldwide means corrosion knowledge is shared internationally. Best practices developed in one country become available globally. Research findings are incorporated into standards that guide practice everywhere. The fight against corrosion benefits from global cooperation and knowledge sharing. And as technology advances and our use of materials evolves, corrosion science evolves with it. Modern corrosion science now extends beyond metals to concrete and composites. For most of history, corrosion meant metal corrosion. But modern construction uses many materials, and all can degrade in ways analogous to metal corrosion. Concrete corrodes, though we usually call it degradation rather than corrosion. The alkaline cement matrix can be carbonated by atmospheric carbon dioxide, lowering pH. Chlorides can penetrate concrete, reaching embedded steel reinforcement and initiating corrosion. Sulfates attack cement, causing expansion and cracking. Freeze-thaw cycles damage concrete in cold climates. The mechanisms differ from metal corrosion, but the result is the same: structural deterioration over time. Composite materials, fiber-reinforced polymers increasingly used in aerospace, marine, and infrastructure applications also degrade. Moisture diffuses into the polymer matrix, weakening the bond between fibers and matrix. UV radiation degrades polymer surfaces. Osmotic blistering occurs when water-soluble species in the composite draw in moisture, creating blisters that delaminate the structure. Modern corrosion science must address all these degradation mechanisms. Researchers study concrete durability, polymer aging, composite delamination, all of these drawing on similar principles and methodologies as metal corrosion research. The electrochemical concepts may not always apply, but the systems approach, understanding environments, materials, protection methods, and monitoring, transfers across material classes. This broadening of corrosion science reflects the diversity of modern materials. We no longer build only with steel and concrete. We use aluminum, titanium, magnesium, composites, ceramics, polymers. Each material has its own degradation mechanisms, and all must be understood and managed. And as our understanding deepens and our tools improve, we can observe corrosion at scales previously impossible. Advanced techniques allow scientists to observe corrosion at the nanoscale. Modern microscopy can visualize individual corrosion pits as they form, watching in real time as atoms dissolve from a metal surface. Electrochemical techniques can measure corrosion currents at specific microscopic locations, mapping out where anodic and cathodic sites form on a surface. Synchrotron X-ray sources can probe corrosion processes with incredible spatial and temporal resolution, showing how passive films form and break down at the atomic level. Electron microscopy reveals the structure of corrosion products in exquisite detail. Atomic force microscopy can map surface topography at nanometer resolution, showing the earliest stages of pit formation. This ability to observe corrosion at the fundamental level is transforming our understanding. We're moving beyond empirical observations. This corrodes faster than that, to mechanistic understanding. This corrodes faster because the passive film has this specific defect structure that allows this particular reaction sequence. With deeper understanding comes better predictive capability. Computer models can now simulate corrosion processes from first principles, predicting how materials will behave in complex environments. These models can guide material development, optimize protection strategies, and explain puzzling field observations. The mystery is yielding to science. What once seemed almost magical. Why some metals resist corrosion while others fail. Why small changes in environment or composition make huge differences in corrosion behavior, is now being explained at the atomic and electronic level. Yet despite all this advancing knowledge and improving technology, failures still occur. Why? Many corrosion failures are predictable and preventable. This is perhaps the most frustrating aspect of corrosion. When investigators examine failures, they often find that the failure was not surprising. The environment was known to be corrosive. The material was known to be susceptible. The protection was inadequate. The inspection was insufficient. The warning signs were present, but ignored. It's not that we lack the knowledge to prevent these failures. It's that the knowledge wasn't applied. Perhaps because of cost pressures, protective measures were seen as too expensive. Perhaps because of schedule pressures, coatings weren't applied properly because the project was rushed. Perhaps because of complacency. The equipment had worked fine for years, so why worry about corrosion now? Or perhaps because corrosion is slow and invisible for much of its progression. It's easy to defer corrosion maintenance. The consequences aren't immediate. The equipment still works. The coating looks acceptable from a distance. So maintenance gets pushed to next year's budget. And next year, there are new priorities and maintenance gets deferred again. Until finally, the accumulated damage causes failure. This is the insidious nature of corrosion. It allows procrastination. It doesn't demand immediate attention the way a fire, or a leak, or a broken machine does. And this makes it easy to underestimate until suddenly it's too late. Which brings us to perhaps the deepest insight of our entire journey through corrosion. The mystery of corrosion is not why it happens, but why we still underestimate it. We understand the electrochemistry, We know the mechanisms. We have protective technologies. We have monitoring methods. We have codes and standards. We have a century of accumulated knowledge and experience. Yet bridges still collapse from corrosion. Pipelines still rupture. Buildings still deteriorate. Aircraft still experience corrosion-related failures. And every year, the global cost remains at trillions of dollars. Why? Because corrosion is patient, and we are not. Because corrosion is persistent, and our attention wanders. Because corrosion is happening everywhere all the time, and we cannot watch everything constantly. Because corrosion costs are distributed across millions of small maintenance items and occasional large failures, making the total impact hard to grasp. Because it's easy to see the benefit of building a new bridge, but harder to see the benefit of maintaining protective coatings on an existing bridge. Because corrosion management requires sustained investment over decades, and institutional memory fades, priorities shift, budgets fluctuate. Because corrosion operates on timescales that don't match human attention spans. A coating might last 10 years. A structure might last 50 years. These are longer than most management tenures, longer than most political cycles, longer than most budget planning horizons. The person who cuts the corrosion maintenance budget isn't around when the structure fails years later. And perhaps most fundamentally, because corrosion is thermodynamically inevitable. We can slow it, manage it, control where it occurs, but we cannot eliminate it. Fighting corrosion requires accepting that the battle is never won, only continuously fought. That's a frustrating reality for humans who want to solve problems and move on. But the battle continues. Must continue. Will continue as long as we build with metals and operate in corrosive environments. As you drift now into the deepest sleep, consider the entirety of our journey. From the ancient discovery that iron rusts, to the scientific understanding of electrochemistry, to the enormous modern costs, to the diverse mechanisms of attack, to the hidden corrosion that surprises us, to the materials that resist and the technologies that protect, to the vigilance required to manage this invisible enemy. Consider the billions spent by militaries to protect fleets and equipment. The space agencies treating corrosion as a mission-critical risk. The coastal infrastructure battling accelerated attack. The standards and knowledge shared globally. The science advancing to nanoscale understanding. The failures that could be prevented if only we applied what we know. The mystery resolves into a paradox. Corrosion is no mystery at all scientifically. We understand it deeply. Yet practically, socially, economically, it remains mysterious. This slow enemy that costs trillions, that we know how to fight but never quite defeat, that we understand yet consistently underestimate. Perhaps the real mystery is human nature. Our tendency to focus on the immediate over the long term, to defer maintenance until crisis forces action, to undervalue the invisible work of prevention, to forget lessons learned as personnel turn over and institutional memory fades. But there is hope. Knowledge continues to advance. Monitoring technologies improve. New materials offer better resistance. Awareness grows as the costs become impossible to ignore. Organizations develop better corrosion management programs. Standards evolve to incorporate new understanding. The battle continues, and while corrosion cannot be eliminated, it can be managed. Infrastructure can last for generations with proper care. Lives can be protected through vigilant inspection. Costs can be reduced through proactive maintenance. The mystery, once understood, need not be a crisis. Rest now. Let all these thoughts settle like sediment drifting down through still water. The electrochemical reactions continue, atoms dissolving, electrons flowing, protective films forming and breaking down, all across the vast infrastructure of human civilization. But systems are in place. People are watching. Protective measures are applied. Maintenance is performed. The vigilance continues. Sleep deeply. Dream, perhaps, of metals that never corrode, of perfect coatings that last forever, of infrastructure that requires no maintenance. These are dreams, impossibilities in our thermodynamic reality, but they're beautiful dreams nonetheless. And when you wake, you'll carry with you a new understanding. You'll see corrosion everywhere now, The rust on an old car, the patina on a copper roof, the coated steel of bridges and buildings, the constant quiet battle being fought to preserve the metal world we've built. You'll understand that every steel structure represents ongoing commitment. That infrastructure is not permanent, but must be continuously maintained. That the price of our metal civilization is eternal vigilance against corrosion's patient, persistent, inevitable attack. The Mystery of Corrosion. 100 facts exploring this phenomenon that shapes our world in ways most people never notice. Now you know. Now you understand. Now, as you drift into dreams, you carry this knowledge with you. The billion-dollar fight against rust continues. The trillion-dollar global cost accumulates. The invisible enemy advances wherever conditions allow. But humanity fights back with science, technology, vigilance, and determination. Sleep well. Rest deeply. The battle against corrosion will still be there tomorrow, as it was yesterday, as it will be for as long as we build with metals in air and water. The mystery is solved. The battle continues. And now, you rest. Good night.